Scania trucks are built with precision inside one of the world's most advanced production lines. From raw steel and giant engines to robotic welding and hand-fitted interiors, every stage is engineered for strength and performance. Today, we go inside the Scania factory to see how cutting-edge machines and skilled workers transform raw materials into powerful trucks that dominate the roads worldwide. Before any assembly begins on the factory floor, months of design and configuration have already taken place through digital modeling and client collaboration. Scania offers thousands of configurations, from cab types and engine sizes to axle arrangements and emissions profiles. Every order is configured down to the most minute specification using proprietary software systems that feed directly into the production planning systems of the factory. This digital integration ensures that each vehicle is built precisely to customer requirements, and it sets the stage for the just-in-time production model that Scania factories are known for. The process truly begins at the component level, starting with the chassis frame, the very skeleton of the truck. These frames are not formed on-site at every assembly plant. Rather, they are usually manufactured at specialized Scania facilities, such as the one in Oskarshamn, Sweden, which is renowned for its advanced laser welding and robotic bending capabilities. The raw material used is high-strength structural steel, delivered in coiled sheets or cut plates from steel mills. These sheets undergo multiple forming processes, including automated press bending, where robotic arms position the steel under immense pressure to form the longitudinal beams that serve as the base of the truck frame. After initial shaping, the steel beams enter a sophisticated robotic welding line. Here, computer-controlled robotic arms move with choreographed precision to apply dozens of welds to each frame component. Each welding head is equipped with sensors that monitor temperature, pressure, and seam alignment in real time. This ensures not only the structural integrity of the frame, but also guarantees a level of repeatability and strength that simply cannot be matched by manual welding. After welding, the frames undergo surface cleaning using shot blasting, a process that fires small steel pellets at high velocity to remove mill scale and other surface impurities, leaving behind a clean, textured finish ideal for powder coating. Next comes the anti-corrosion treatment, which is absolutely vital given the operating environments that Scania trucks face globally. The prepared frame is dipped into large immersion tanks containing anti-corrosive coatings. These coatings bond to the steel surface and offer long-term protection against rust and environmental wear. Once coated, the frame is cured in high-temperature ovens to ensure the treatment hardens properly and maintains adhesion through the vehicle's life cycle. While chassis frames are being processed, the cab structure, the cockpit of the truck, is being built in parallel. Scania's cab production is typically handled in highly automated body shops. The core of the cab begins as pressed steel panels that are stamped into shape using massive hydraulic presses. Each press can apply hundreds of tons of force, transforming flat sheet metal into complex structural elements like roof panels, side walls, and floor pans. These pressed panels are then moved by robotic arms into positioning jigs where they are tack welded together to form the basic cab shell. The welding of the cab shell is another highly automated process. Industrial robotic arms, fitted with multiple welding torches, navigate around the jig to apply hundreds of spot welds with exacting precision. Sensors track the positioning down to millimeter level tolerances, ensuring every cab structure is perfectly square and secure. As with the chassis frame, once the cab shell is fully welded, it is subjected to shot blasting and anti-corrosion dipping. After treatment, the cab shell is baked in industrial curing ovens and then passed into the next phase, painting. The painting process is one of the most visually striking steps in the factory. Trucks are typically painted in customer-specific colors, and Scania's paint shops are designed to switch colours rapidly with minimal waste. First, the cab shell enters a cleaning station where it is rinsed, degreased, and coated with a phosphate layer to promote paint adhesion. Next, it enters the electrocoating tank, a large bath filled with a water-based paint solution that is electrically charged. The cab is submerged and an electrical current is applied, causing paint particles to bond electrochemically to the metal surface in a uniform layer. This electrocoat layer is corrosion resistant and acts as a primer for the top coat. Once cured in an oven, the cab shell enters the colour booth. This area is a climate-controlled environment where automated paint robots, guided by 3D scanning systems, apply base coat and clear coat layers with astonishing accuracy. The robotic arms mimic human wrist movements, but with far more consistency and speed. Depending on the finish, additional layers like metallic flakes or special high-gloss coatings may be added. After painting, the cab passes through a final curing oven, where the coating is hardened under controlled heat conditions. While the cab and chassis are progressing through their respective lines, work begins on the engine, the heart of every Scania truck. Scania is known globally for manufacturing its own engines, and the engine assembly takes place in facilities with a near-surgical level of cleanliness. Engine blocks arrive from foundries where molten iron has been cast into precisely machined forms. These blocks are cleaned, inspected, and then sent through CNC machining lines to be drilled, bored, and honed. Critical components like cylinder bores, oil channels, and mounting faces are machined to micrometer level tolerances to ensure proper sealing and performance. The engine assembly line is a hybrid of human craftsmanship and automated precision. Components like the crankshaft, camshaft, pistons, and connecting rods are assembled using semi-automated workstations where torque-controlled tools tighten bolts to exact specifications recorded in a central database. Scania engines are known for their modularity. Many of the components can be shared across different engine variants, simplifying logistics and repair. Each engine is assembled in stages, with sensors and barcode tracking, ensuring that every step is validated before moving to the next station. Once the engine is fully assembled, it moves to the hot test cells, where it is connected to a computerized test rig and run under simulated load conditions. These test cycles verify oil pressure, emissions output, power delivery, and temperature control. The engine must pass every parameter before it is certified for installation. Failures are extremely rare due to the high degree of automation and quality control earlier in the process. By this stage in the production process, the frame, cab, and engine are all nearly complete. The next phase is the main assembly line, a linear path where all major components are brought together. This line stretches hundreds of meters through the heart of the factory and is divided into dozens of stations, each with a specific responsibility. Trucks move along the line on large powered platforms or guided vehicles, allowing workers and robots to access all sides without repositioning. The first step on the assembly line is the chassis outfitting, where the bare steel frame receives mounting brackets, fuel tanks, air tanks, electrical conduits, and brake lines. Each part is pre-assembled into kits that arrive from sub-assembly areas and are bolted on using torque-controlled tools. Workers scan every part's barcode into the digital tracking system, ensuring complete traceability from installation to delivery. As the chassis assembly progresses down the main line, the stage is set for one of the most critical moments in the truck's birth: the installation of the drivetrain. This includes the mounting of the engine, transmission, clutch assembly, and propeller shafts, all aligned and fitted with micrometer precision. The engine, having already passed its hot test, arrives at the drivetrain installation zone pre-mounted on a subframe cradle. This subframe allows the engine to be maneuvered easily and with extreme accuracy. Overhead, automated hoists fitted with dynamic positioning systems gently lower the engine into the frame rails. A laser-guided alignment system ensures that the engine mountings perfectly match the pre-fitted brackets on the chassis. At this point, technicians, supported by robotic arms that hold the engine weight, secure the mounting bolts using calibrated torque wrenches. Every bolt torque is recorded and logged digitally to create a traceable quality certificate tied to the vehicle's serial number. Following engine installation, the gearbox, a heavy and complex component, is hoisted into position behind the engine. Scania often uses its own automated manual transmissions, which integrate seamlessly with the engine via a robust clutch assembly. The clutch mechanism is pre-aligned with the flywheel, and the entire transmission unit slides onto guide pins with barely a millimeter of clearance. Here, technicians connect the hydraulic lines, gear linkages, and electrical connectors that allow for automated gear shifting, engine brake interaction, and adaptive cruise functionality. With the drivetrain in place, attention turns to the rear axle and suspension systems. Depending on the truck's intended use, long-haul, construction, or specialized applications, different axle configurations are applied. Some trucks feature a single rear axle, while others utilize tandem configurations or even additional tag axles. The axles arrive pre-assembled from Scania's axle plant, complete with brakes, hubs, and suspension linkages. They are lifted into place by hydraulic jacks and bolted to the chassis with spring packs, air bellows, or hydraulic suspension systems already integrated. Next comes propeller shaft installation, connecting the transmission to the rear axles. These shafts are balanced dynamically at the supplier's facility to prevent vibration. Universal joints are fitted with greased couplings and protective covers, ensuring long-term durability under high torque loads. At this point, the foundation of the truck's powertrain is complete. However, without electrical and pneumatic systems, the vehicle would remain lifeless. The next station handles electrical harnessing and air system integration. Scania trucks feature an extensive network of electrical harnesses, connecting everything from the engine control module and dashboard to rear light clusters and sensors. These harnesses are laid out in custom configured looms that match the specific vehicle configuration. Workers unroll and clip these looms into pre-installed brackets along the chassis rails, securing them with fasteners and protective sheathing. The plugs and connectors are then checked for correct mating, and a low-voltage continuity test is performed to validate the integrity of each circuit. In parallel, technicians install air hoses and pneumatic control lines, crucial for the operation of brakes, suspension, and gear shifting systems. Scania uses color-coded hoses for easy identification: blue for service brakes, red for emergency lines, yellow for auxiliary systems. The hoses are pressure tested before installation and connected to manifold blocks fitted with quick-release couplings. Once in place, the entire pneumatic system is subjected to a leak-down test using compressed air. Pressure sensors monitor the rate of decay, and if it exceeds a predefined threshold, technicians isolate and rectify the issue before the vehicle proceeds. With the chassis now wired, plumbed, and powered, the moment arrives for the cab to be mounted. The painted and primed cab shell, now fully treated and cured, has been proceeding through a parallel line where interior components are added. Before it is even lifted onto the chassis, the cab undergoes pre-fitting of the dashboard, insulation, wiring, and climate control systems. The dashboard arrives as a single pre-wired module complete with instrument cluster, infotainment unit, control switches, and HVAC ducting. It is installed into the cab using a robotic arm that slides the assembly into its predefined slots and secures it with vibration-resistant fasteners. At this stage, seats, pedal boxes, steering columns, and interior trim pieces are installed by skilled technicians. Each element is configured based on customer preferences, from seat fabric and placement to storage compartments and auxiliary switches. Once the interior is complete, The cab is transported via an overhead conveyor to the cab marriage station, a precise and dramatic point in the assembly process. Here, a massive cab lifting robot equipped with multi-axis movement positions the cab above the chassis. Using laser alignment sensors and pre-programmed coordinates, the system lowers the cab onto 4 chassis mounting points. Pneumatic mounts or mechanical bushings are inserted to dampen vibrations and provide ride comfort. Once seated, high-strength bolts are applied with synchronized torque tools, and the cab becomes one with the chassis. Following this, technicians connect the main wiring harness and pneumatic lines from the cab to the chassis, a process known as cab-chassis interface. These connections include CAN bus data lines, power feeds, brake system controls, and auxiliary switches. As soon as these connections are complete, the vehicle is able to wake up electronically for the first time. A diagnostic tablet is plugged into the OBD port and the truck performs a systems check. Any discrepancies or error codes are logged and addressed before the truck moves forward. The vehicle now advances to the fluid filling and commissioning station. Here, all essential fluids are added, including engine oil, coolant, transmission fluid, brake fluid, power steering fluid, AdBlue, and diesel fuel. Each fluid fill station uses metered pumps that log exact fill quantities and pressure levels. Automated sensors inside the engine and tank systems confirm that fluid levels are within range before proceeding. Once filled, the truck moves to the initial startup station, where the ignition is switched on for the first time on the line. The starter motor cranks the engine, which should come to life smoothly. A team of technicians monitors engine performance, checking for warning lights, irregular noise, or leaks. The air compressor charges the brake system, and all pneumatic circuits are tested for function. This includes pressing the brake pedal, triggering the parking brake, and cycling the air suspension. Next, the truck undergoes a dynamic rolling road test inside a fully enclosed test chamber. The vehicle is driven on rollers that simulate real-world road resistance, while various systems are tested under load. This includes acceleration tests, ABS brake tests, gear shifting patterns, cruise control behavior, emission system feedback, and traction control activation. The data is streamed in real time to diagnostic software, where engineers verify that the truck operates within all calibrated parameters. Upon passing the rolling test, the truck is driven into the final inspection bay. Here, inspectors conduct a detailed walk-around, checking for cosmetic imperfections, paint defects, missing trim pieces, or loose fittings. Each headlight, indicator, fog lamp, and brake light is checked for functionality and alignment. Mirrors are adjusted, windscreen wipers tested, and all cabin electronics, including navigation, air conditioning, radio, and USB ports are verified for operation. Once the final inspection is complete, the vehicle moves to the finishing line, where customer-specific decals, model badges, and optional accessories like bull bars, sun visors, or additional lighting rigs are added. Every Scania truck is tailored to its owner's vision, and this station gives each one its unique identity before it leaves the factory. The completed truck now rolls into the validation and delivery area, where all data from the manufacturing process, component serial numbers, torque values, diagnostic results, and inspection records are compiled into a digital certificate of compliance. This certificate accompanies the truck throughout its life, acting as a birth record for servicing and warranty purposes. At this point, the truck is technically complete, but its journey is far from over. In the next section, we will follow how Scania handles post-factory logistics, transport, dealer preparation, and delivery to the end customer, along with insights into technological innovations and modular production strategies that continue to shape Scania's dominance in global trucking. Once the truck passes its final on-site validation and is cleared for delivery, it enters a new phase in its life cycle: post-factory logistics and outbound handling. This transition is just as carefully orchestrated as the build itself. A Scania truck may be fully assembled, tested, and polished, but before it can reach the customer, it must navigate a labyrinth of post-production processes including staging, transport planning, documentation handling, and final handover preparation. This stage marks the convergence of manufacturing precision and supply chain excellence. The first step in this process is vehicle staging, which occurs in a designated outbound yard adjacent to the factory. This outdoor staging area is organized with military-grade precision, divided into zones based on delivery destination, vehicle type, and shipping method. Trucks are driven, not towed, from the final inspection area to the appropriate staging bay. Each vehicle is equipped with temporary wheel covers and protective wraps over vulnerable surfaces like mirrors, windshields, and chrome trim. These protective measures prevent damage during transport, especially when trucks are carried on open trailers or cargo vessels. In the outbound yard, every truck is again scanned using RFID and barcode systems, confirming its identity and correlating it with a live logistics management system. This software tracks all trucks awaiting dispatch and organizes them according to optimal shipping schedules. Depending on the final destination, a truck may be routed for domestic road delivery, loaded onto a rail car, or prepared for maritime shipment if it's headed overseas. Each route comes with its own handling protocols. For domestic deliveries within Europe, trucks are often driven under their own power by certified logistics drivers. These drivers, trained in Scania vehicle systems, are responsible not only for transportation, but for monitoring the vehicle en route. Before leaving, they perform a second-round walk-around inspection, checking fluid levels, tire pressures, and verifying that the truck matches its shipping manifest. Each journey is GPS tracked and time logged, ensuring total visibility for the customer and Scania's distribution center. If the truck is destined for international export, the logistics become more complex. Vehicles headed for distant markets like South America, Asia, or Africa are transported in batches, often using ro-ro vessels, or roll-on/roll-off ships. Prior to shipment, trucks undergo a pre-export treatment. This includes draining fuel to a minimum safe level, checking emission systems to meet port regulations, and applying additional weatherproofing layers to vulnerable components. If local regulations require specific emissions calibrations or market-specific software updates, these are applied at this stage by an outbound technician using a portable diagnostics tablet. Trucks bound for shipping are driven onto specialized transporters and secured with heavy-duty wheel chocks and tie-down systems. These transporters then carry them to port terminals, where logistics partners manage loading onto ro-ro decks using low-speed maneuvers to protect drivetrains. Throughout this entire handover process, every movement is tracked, and a digital chain of custody is maintained. In some cases, vehicles are not shipped fully assembled. For certain regions with import restrictions or high shipping costs, Scania employs a CKD strategy, complete knockdown. In this method, trucks are partially disassembled after factory completion and packed into containers, then shipped to regional assembly centers. Here, local teams reassemble the trucks under supervision, with full adherence to Scania's engineering and quality standards. This allows Scania to maintain a global footprint without needing a full manufacturing line in every country. Back in Europe, however, trucks that remain in their final configuration are delivered either to regional logistics hubs or directly to dealerships, depending on customer contracts. These logistics hubs serve as a final buffering point before customer delivery. Here, each truck is cleaned again, checked for any transport damage, and in some cases, fitted with market-specific accessories like tachographs, radio equipment, or fleet telematic systems. These are often added just before delivery to ensure compliance with local transport laws or client specifications. Once the vehicle reaches a Scania dealership or customer depot, a final pre-delivery inspection, or PDI, is conducted. This check is performed by certified dealer technicians who cross-reference the vehicle's production history with a detailed checklist covering all operational systems. This includes cabin electronics, tire and wheel torque, headlight alignment, climate control operation, door seals and warning systems. Any required updates to onboard software, such as navigation databases or telematics modules, are downloaded and installed. At this point, the truck is nearly ready for handover to the customer, but Scania doesn't simply hand over the keys. For fleet clients or first-time buyers, a dedicated Scania delivery specialist may conduct a full walkthrough of the truck's systems. This includes explaining the adaptive cruise control functions, emergency braking systems, lane departure warnings, engine braking modes, and fuel-saving strategies. Drivers are often given a demonstration of how to use Scania's onboard telematics system, known as Scania Fleet Management, which allows fleet operators to monitor fuel consumption, driver behavior, vehicle health, and maintenance schedules in real time. This entire process, from component welding to client delivery, is only possible due to the extraordinary level of digital integration within Scania's production and logistics ecosystem. Every part, process, and movement is connected through a unified IT platform that synchronizes planning, inventory, production, and outbound delivery. This digital backbone allows Scania to offer mass customization at industrial scale, which is rare in heavy vehicle manufacturing. Beyond the sheer logistics of delivery, what truly sets Scania apart is its modular architecture, a production strategy that deserves closer inspection. Unlike many truck manufacturers that rely on rigid product lines and bespoke configurations that increase complexity, Scania uses a tightly controlled system of shared components and scalable designs. For instance, the same type of engine block can be used across multiple power ratings, with changes in turbocharging, fuel injection mapping, or transmission pairing creating different performance profiles. Cab shells also share mounting points, crash structures, and roof lines, with final variations created through bolt-on panels, interiors, and accessories. This modularity dramatically reduces the number of unique parts required on the factory floor, streamlining logistics and reducing time between customer order and vehicle build. It also ensures that spare parts are widely compatible, simplifying aftermarket servicing and reducing downtime for fleet operators. For Scania, modularity is not just a design choice. It is a strategic manufacturing philosophy that underpins everything from tooling and robotics to workforce training and dealer support. Inside the factories, this approach enables a high degree of automation. Robotic systems handle repetitive, precision-critical tasks such as welding, painting, and component fastening. Yet the human role remains central, especially in final assembly, inspection, and troubleshooting. Scania invests heavily in worker training, with programs that teach technicians how to read digital work instructions, use torque validation tools, and interpret real-time diagnostics data from vehicles in production. These skills are critical in maintaining quality across a product range that offers nearly infinite customization. To further enhance efficiency and quality, Scania has implemented smart factory technologies, including IoT sensors embedded throughout the production line. These sensors monitor equipment status, production flow, and product quality in real time. If a robotic welding arm shows signs of drift, or if a torque gun applies a value slightly out of spec, the system alerts supervisors instantly. Predictive maintenance algorithms analyze these data streams to prevent unplanned downtime, allowing equipment to be serviced before failure occurs. Sustainability is another cornerstone of Scania's manufacturing model. The company has made major investments in reducing the environmental impact of its facilities. This includes using renewable electricity, water recycling systems in paint shops, and closed-loop material recovery processes. For instance, steel offcuts from cab panel stamping are collected, sorted, and returned to suppliers for reprocessing. Paint overspray is captured and filtered before it reaches the atmosphere, while heat generated by curing ovens is recycled to warm nearby buildings. Even the logistics fleet used to move trucks from plant to port has undergone greening. Many Scania factories use their own battery electric or gas-powered truck transporters for short-range movements, reducing emissions around the factory campus. Scania's long-term goal is to create a fossil-free value chain, meaning not just fossil-free trucks, but a zero-emissions process behind every vehicle's creation. What emerges from all of this is not just a truck, but a precision-built, software-integrated, environmentally conscious transport machine designed to serve its owner with maximum uptime and minimum operating cost. Every bolt torqued, every panel painted, and every test completed is done with the understanding that this machine will soon be barreling down highways, climbing mountains, or navigating mines, often in the most demanding environments on Earth. And so, as a freshly built Scania truck pulls out of the outbound lot under its own power, fully tested, aligned, and gleaming in its custom livery, it carries with it not just cargo, but a legacy of Scandinavian engineering, lean production mastery, and digital age innovation. As the newly minted Scania truck rolls off the assembly line and onto the road, its journey as a manufactured product may be complete, but its role as a data-rich, high-performance logistics tool is just beginning. What differentiates Scania in the world of heavy-duty vehicles is not just its robust physical engineering, but also the intelligent integration of software and digital systems embedded throughout the truck. These features are not just bolted on at the end of production. They are enabled and supported throughout every stage of the manufacturing process. At the heart of this smart infrastructure is the Scania Communicator, a telematics control unit installed during the cab outfitting phase. This device connects the truck to Scania's fleet management system and remote diagnostics platforms. It functions as a two-way communications gateway between the vehicle and Scania's global network, transmitting real-time data on vehicle health, driver behavior, location, and fuel consumption. While the physical hardware is relatively compact, its installation is incredibly precise. During assembly, technicians route antennae, signal cables, and CAN bus interfaces through pre-designed channels in the cab, ensuring electromagnetic compatibility and resistance to vibration. The communicator's integration enables predictive maintenance, a significant evolution in vehicle lifecycle management. Throughout operation, the truck continuously monitors dozens of performance parameters: oil pressure, coolant temperature, brake wear, turbocharger pressure, emission levels, and more. These data points are compared against factory thresholds, and if any system approaches a condition that could cause failure, an alert is generated. This could trigger anything from a simple driver notification to a pre-scheduled service appointment at the nearest Scania workshop. It is a direct result of a factory design philosophy where the vehicle's digital nervous system is assembled and validated just as rigorously as its mechanical one. Alongside predictive maintenance, the truck's electronic control systems, also installed and configured on the assembly line, provide a high level of operational automation. Modern Scania trucks are built with dozens of ECUs, each responsible for a specific subsystem such as engine management, brake control, transmission logic, and climate systems. These units are connected via a redundant CAN network architecture, which not only increases fault tolerance, but also simplifies diagnostic procedures. During production, technicians use factory-grade diagnostic terminals to flash the appropriate firmware to each ECU, calibrate its behavior based on the truck's configuration, and verify communication across the entire electronic network. Scania's modular philosophy also extends to advanced driver assistance systems, many of which are pre-installed on the production line but activated or configured according to the customer's specifications. For example, the radar sensors used for adaptive cruise control and autonomous emergency braking are mounted on the front bumper during final assembly, precisely aligned to maintain millimeter-level accuracy over the vehicle's life. Similarly, the forward-facing camera that enables lane-keeping assistance is fitted behind the windshield during cab assembly, carefully positioned with a jig to ensure a clear, centered field of vision. Once installed, these components are connected to a centralized ADAS controller, which interprets sensor input and makes real-time driving decisions. These systems are subjected to a suite of calibration and alignment procedures before the truck leaves the factory. On the test track, radar and camera systems are validated against standard reference objects and road markers. In a controlled environment, the truck is driven through a calibration tunnel equipped with reflective targets, road signs, and lane markings designed to simulate real-world conditions. The vehicle's onboard systems must correctly interpret these stimuli, and if any discrepancies are found, technicians adjust sensor positioning or recalibrate software parameters using diagnostic interfaces. The cab interior too reflects a fusion of mechanical craftsmanship and digital design. Every detail, from the curvature of the dashboard to the responsiveness of touchscreens, is a result of ergonomic research and industrial design thinking. Scania recognizes that its drivers may spend days or even weeks living inside their cabs, and thus the manufacturing process treats the interior not just as a workplace, but as a living space. During cab outfitting, highly trained technicians assemble a range of custom options, from sleeper bunks and refrigerators to infotainment systems and integrated GPS navigation units. These elements are delivered to the line in kit form, each kit tailored to the customer's build sheet. Each cab interior is assembled under tightly controlled conditions to minimize dust, moisture, and static electricity, which could interfere with sensitive electronics. Seats are bolted to reinforced mounting points welded into the cab shell during body assembly, and each one is torque checked and height adjusted based on ergonomic templates. Touchscreen interfaces and instrument clusters are plugged into the vehicle's central network and tested via digital loopback to ensure correct display and input functionality. The HVAC system, including its filters, ducting, and thermoelectric units, is pressure tested and leak checked using nitrogen injection methods before being approved for operation. Another layer of sophistication is found in Scania's drive mode management system, also programmed during the production process. Depending on the truck's intended use, long-haul highway driving, urban logistics, construction haulage, or extreme terrain operation, the engine and transmission control units are calibrated to optimize for performance, fuel economy, or torque delivery. These calibrations are not simple throttle mappings. They include dynamic interaction between acceleration profiles, shift timing, exhaust gas recirculation rates, and even cooling fan activation thresholds. Engineers use proprietary software tools during assembly to upload the correct strategy maps into each ECU and then perform a synchronization cycle, ensuring all systems operate under a unified logic framework. In high-performance applications, such as off-road or heavy load logistics, the truck may also be equipped with retarders, differential locks, and terrain modes. These features are controlled by modules installed under the dashboard and linked to the vehicle's main control network. Their installation involves not just physical mounting, but precise firmware configuration and sensor calibration. For instance, the differential lock actuator includes a position sensor that must be zeroed against the axle's true neutral position during installation. Once installed, these systems are tested during the dynamic run phase to ensure they engage and disengage correctly under simulated load. Meanwhile, aerodynamic elements such as roof deflectors, side skirts, and underbody fairings are installed toward the end of the main assembly line. These parts are often lightweight composite materials and are affixed using vibration-dampened fasteners and adhesive compounds designed to withstand high-speed airflow and temperature fluctuations. Their role in fuel economy is non-trivial. Even minor misalignments can increase drag, so final inspection stations are equipped with laser-guided measuring tools to verify exact positioning. Assembly teams cross-check these with 3D digital overlays displayed on large screens at the workstation. Beyond the truck itself, the factory also assembles and configures support technologies such as Scania Zone and Scania Driver Support. These tools are software-based but rely on correctly installed hardware during production. GPS modules, accelerometers, and vehicle-to-infrastructure communication units. Once activated, these systems allow operators to set geofenced zones where speed, emissions output, or engine performance is automatically regulated based on environmental or regulatory constraints. All of this logic is programmed through cloud-based platforms, but it depends entirely on the integrity of the installation work completed on the factory floor. Scania's embrace of digitalization also includes its end-of-line analytics systems, which collect every data point recorded during the truck's production. These include sensor calibrations, fluid fill quantities, software versions, torque readings, and test drive results. Once the truck completes its final quality checks, all this information is compiled into a digital build certificate, stored in Scania's central server network. This certificate not only proves the vehicle's compliance with legal standards, but it also becomes the backbone for future updates, diagnostics, and warranty assessments. Because of this meticulous build documentation, over-the-air updates can be rolled out to Scania trucks even after they have left the factory. The communicator module facilitates this functionality, allowing engineers to deploy firmware improvements, bug fixes, or performance upgrades without requiring the truck to return to a service point. This capability, made possible only because the production process embeds software management from the beginning, is rapidly becoming a key differentiator in the world of commercial transport. Perhaps most impressively, all of this technological complexity is achieved without sacrificing modularity, durability, or long-term serviceability. That's because every element, from wiring looms and ECUs to cab panels and control switches, is installed with future maintenance in mind. Harnesses are routed through accessible channels, ECUs are mounted in service boxes, and diagnostic ports are placed in standardized locations regardless of configuration. This consistency allows Scania dealers worldwide to service a wide variety of truck models with a common toolset and shared training, reducing cost and maximizing uptime for operators. The sum of all these innovations, from embedded sensors and adaptive software to modular electronics and digital infrastructure, is a Scania truck that operates not merely as a mechanical platform, but as a living, communicating system capable of learning, adapting, and reporting throughout its operational life. This vision of the modern truck as a responsive and evolving tool is deeply rooted in the manufacturing philosophy that builds it. A philosophy where every bolt, sensor, and wire is installed with purpose, tested with rigor, and documented with precision. Behind every meticulously crafted Scania truck lies a vast, highly organized human and mechanical ecosystem, an integrated workforce structure combined with world-class lean production methodologies. These systems are designed not only to uphold the brand's legendary quality standards, but to continuously improve them, model after model, day after day. While the end product might be steel, rubber, glass, and code, the beating heart of Scania's manufacturing process is its people and the smart systems they use. Scania's factory workforce is divided into several highly specialized roles, each optimized for a specific part of the assembly line or manufacturing process. These include welders, material handlers, electronic assembly technicians, test engineers, paint technicians, quality controllers, and logistics coordinators, among others. However, what truly distinguishes the Scania workforce is not rigid job segregation, but a dynamic cross-functional approach. Many workers are trained across multiple disciplines and encouraged to rotate tasks, which fosters a deeper understanding of the entire truck building process and enables agile response when production demands shift. This flexibility is essential because Scania operates under a pull-based production system, a fundamental component of its lean manufacturing strategy. Rather than producing trucks in large batches based on forecasted demand, Scania builds each truck to order, with every unit reflecting a unique customer configuration. When a client places an order, that request propagates through Scania's production planning system, triggering a cascade of component manufacturing, subassembly preparation, and final assembly scheduling. Every workstation on the line is updated with this incoming configuration data in real time, enabling the workforce to prepare for exact variations even before the chassis reaches their station. To manage this complexity, Scania employs a cell-based manufacturing layout, particularly in cab and engine subassembly. In this model, small autonomous teams, called production cells, take full ownership of assembling specific components or systems. Each cell is responsible not just for assembly, but also for quality control, minor maintenance of their equipment, and implementing continuous improvement initiatives. Workers within these cells hold daily stand-up meetings to review performance metrics, quality issues, and improvement suggestions. These meetings are an embodiment of Scania's commitment to Kaizen, or continuous incremental improvement. This improvement philosophy is not left to chance. Scania empowers its workers with structured frameworks like the Scania production system, a variant of the famed Toyota production system, adapted for the unique challenges of modular truck manufacturing. SPS is built around key principles like right from me, demand-driven flow, and standardized work with flexibility. Each station has visual boards displaying production targets, current throughput, quality alerts, and safety metrics. Any worker, at any time, can pull an andon cord, a signaling mechanism that immediately halts production to address a problem or anomaly. Far from being penalized, such actions are encouraged, reinforcing a culture of quality ownership. SPS also ensures that work instructions are standardized and digitized. At every station, touchscreens provide step-by-step guidance for each unique truck configuration, including diagrams, torque settings, part numbers, and even short instructional videos. This system ensures consistency, even when different workers or shifts are involved. It also supports the introduction of new model variants or upgraded parts, as digital updates can be rolled out instantly across the entire facility. But the factory's brain doesn't stop at the workstation level. Scania's facilities are organized using advanced logistics and material replenishment systems. These include just-in-time and just-in-sequence delivery models. In the JIT approach, components arrive at the assembly line exactly when needed, reducing on-site inventory and waste. JIS takes this a step further by ensuring that parts not only arrive on time, but in the exact order the assembly line requires them, matching the customer-specific build schedule. To make this possible, Scania utilizes autonomous guided vehicles and collaborative robots, also known as cobots. AGVs are programmed to navigate specific paths throughout the facility, transporting parts, kits, and tools from storage to workstations. These mobile units are equipped with obstacle detection sensors and onboard computers, allowing them to safely navigate busy factory environments and prioritize urgent deliveries. Cobots, on the other hand, work directly alongside human operators. They handle tasks like component positioning, torque application, and small part assembly. Because cobots are designed to operate safely around people, they can perform repetitive precision tasks while allowing human workers to focus on complex, decision-making, and quality assessments. One of the most advanced implementations of lean philosophy at Scania is its digital twin system. This virtual representation of the entire truck assembly process allows engineers and planners to simulate workflows, test layout changes, and even trial new product designs in a fully digital environment before committing changes to the physical factory floor. These simulations integrate real-world production data, making them incredibly accurate and predictive. Before a new model is introduced, it is built and validated in this digital environment, ensuring the tools, workstations, and instructions are perfectly prepared for real-world production. The importance of training and workforce development cannot be overstated in this high-performance environment. New employees go through comprehensive onboarding programs, including virtual reality training simulations, where they practice assembly techniques and safety procedures in a risk-free setting. More experienced workers have access to continuing education through Scania's in-house training academy, which covers topics such as electronics diagnostics, sustainability practices, robotics programming, and leadership development. These programs ensure that Scania's workforce remains adaptive, skilled, and deeply connected to the company's long-term goals. Scania's commitment to sustainability extends well beyond the trucks it produces. It's embedded in the very operations of its factories. Each manufacturing site is governed by a green production strategy, which includes aggressive targets for energy efficiency, waste reduction, and carbon neutrality. Solar panels line the roofs of production buildings, and in several sites, geothermal energy or district heating is used to manage interior climate control with minimal environmental impact. Water used in paint shops and testing areas is filtered and recirculated using closed-loop systems, reducing freshwater usage dramatically. Waste from steel stamping, machining, and welding operations is meticulously sorted and sent back to steel suppliers for recycling, creating a circular materials economy. Even the packaging used for inbound components is standardized and reusable. Suppliers ship parts in containers that are returned, cleaned, and reused repeatedly. Scania's internal logistics fleet, used to move materials between factory sites and distribution hubs, now includes electric trucks and vehicles powered by biofuels, reducing the carbon footprint of interfacility transport. Each of these sustainability initiatives is audited and quantified, with progress reported in annual sustainability disclosures. The factories themselves are certified to international standards such as ISO 14001 for environmental management and ISO 50001 for energy management, ensuring that improvements are not only achieved but institutionalized. These practices aren't just good for the planet, they're good for production. Energy-efficient lighting, heat recovery systems, and smart building automation lower operating costs, which ultimately contribute to Scania's competitive advantage in manufacturing. Moreover, by reducing the environmental footprint of its operations, Scania aligns itself with the increasingly stringent regulatory demands in global markets, ensuring compliance without last-minute adaptation or retrofitting. But lean and green aren't the whole story. Scania also embraces operational transparency and external collaboration. Factory tours are not uncommon, not just for public relations, but for academic, industrial, and supply chain partners. These visits are carefully choreographed but open in intent, demonstrating Scania's willingness to share best practices and invite scrutiny. Likewise, feedback from suppliers, service technicians, and even end users is fed back into the production process. If a common failure mode or service complaint emerges from the field, engineers collaborate directly with line workers to trace root causes and implement corrections, sometimes within days. This culture of bottom-up innovation is rare in large-scale manufacturing, but thrives at Scania. Workers are encouraged to submit improvement suggestions, known internally as yellow cards, through a structured feedback mechanism. These ideas can range from tool redesigns and safety enhancements to procedural changes that save time or reduce fatigue. Implemented ideas are celebrated in team meetings, and successful contributors are rewarded not just with recognition, but often with career advancement opportunities. The ultimate outcome of all this is a manufacturing operation that is resilient, adaptable, and deeply human-centric, despite the heavy use of automation and digital systems. Each truck, though shaped by machines and moved by algorithms, bears the unseen fingerprints of hundreds of skilled individuals who have each left a mark on its creation. It is a deeply collaborative process where man and machine act not in opposition, but in orchestration. The story of an H2R does not begin on the assembly line. It begins much earlier, within the metallurgical divisions and materials labs that prepare the raw constituents of the motorcycle's essential components. At this initial stage, the journey starts with a block of high-tensile steel alloy, specifically formulated for the H2R's trellis frame. This isn't ordinary steel. Kawasaki engineers designed the alloy composition to maximize tensile strength while balancing torsional rigidity and ductility. Sheets and tubing are delivered to the fabrication facility in precisely measured cuts, each one traced through an internal lot tracking system for complete traceability. Within the factory, the raw frame tubing undergoes cold drawing, a process that pulls the steel through dies to fine-tune its dimensions and surface integrity. Cold drawing is chosen specifically because it preserves mechanical strength while yielding tight dimensional tolerances, which are critical for the trellis frame's intricate geometric structure. Robotic armatures position each steel tube beneath automated laser cutting heads that slice the tubes into exact segments, using CNC-defined angles to ensure proper later fitment during welding. The accuracy here is staggering. Deviations beyond 0.1 millimeters trigger alerts in the system, halting the production cell for inspection. These cut tubes are then transferred via automated conveyors to a robotic frame welding station. Unlike mass-market motorcycle frames, the H2R's frame is entirely hand-welded, albeit with robotic support for fixturing and alignment. Skilled technicians, each trained for months on frame-specific geometries, perform manual TIG welding to fuse the chromoly steel components together. This welding process isn't just about joining metal. It's a delicate operation, balancing thermal input and cooling rates to avoid internal stress or warping, which could compromise high-speed stability at over 300 kilometers per hour. Once the frame is assembled, it enters a dimensional verification stage utilizing 3D laser scanning. The scanning head, mounted on a 6-axis robotic gantry, creates a digital twin of the physical frame, comparing it to the original CAD model within fractions of a millimeter. If the frame passes all checks, it moves to a powder coating line where it is electrostatically coated and oven cured at controlled temperatures. The specific gloss and hardness of the black frame coating are chosen for both heat resistance and resistance to rock chips and vibration-induced wear. Meanwhile, in another section of the plant, the supercharged engine, the beating heart of the H2R, begins its life in the engine assembly hall. This hall is a restricted environment, temperature and humidity controlled, and acoustically insulated from the rest of the plant. The reason is simple. The inline 4-cylinder engine that powers the H2R is not just another power plant. It's an ultra-high performance 998cc unit, force-fed by a centrifugal supercharger capable of spinning at up to 130,000 RPM. Such precision demands a sterile, meticulously maintained production environment. Engine block castings arrive from Kawasaki's dedicated foundry, having been machined to spec using 5-axis CNC centers. These blocks are inspected using ultrasonic resonance techniques to detect subsurface anomalies that cannot be seen visually or through surface scanning. If the casting passes inspection, it is mounted onto an engine cradle fixture, and the first stage of assembly begins. The installation of crankshaft bearings. Each bearing shell is hand micrometered and color-coded marks are applied to designate their oil clearance class. This step is crucial because the H2R engine tolerances are far tighter than in commuter bikes. The goal is minimal oil film thickness for maximum responsiveness without inducing friction-related failures. After the bearings are installed, the forged steel crankshaft is delicately lowered into the block. This crankshaft, balanced to aerospace-grade tolerances, is laser etched with its unique serial number for tracking and quality assurance. Next, titanium connecting rods and forged pistons are assembled offline on dedicated piston rod mating benches. Each piston is weighed and matched to its rod to within 0.5 grams to ensure uniform reciprocating mass balance. Piston rings are installed using rotary ring expanders that ensure even pressure and no deformation. The piston assemblies are then inserted into the engine block using hydraulic-assisted ring compressors, and the crankshaft is rotated by hand through a flywheel fixture to ensure smooth, unimpeded movement. Even the tiniest resistance would be flagged as an indicator of misalignment or contamination. Once the bottom end is secured and torqued in a cross pattern using digitally calibrated torque wrenches, attention shifts to the cylinder head. The H2R cylinder head is a complex component, machined with pent roof combustion chambers, large titanium valves, and dual overhead camshafts. Valve springs are installed using a pneumatic valve spring compressor, and valve lash is adjusted using precision shims measured to within hundredths of a millimeter. Camshafts, hardened and micro-polished, are mounted on journal caps and rotated to align with timing marks on the crank. The timing chain, a double roller unit, is fed through a guide channel and connected to the crank sprocket, then tensioned using a hydraulic chain tensioner preloaded with assembly oil. Once aligned, the engine is rotated again by hand, and valve timing is confirmed using a laser cam phase analyzer that calculates exact intake and exhaust overlap degrees. Now comes the installation of the supercharger, the defining feature of the H2R. The supercharger is assembled in a separate clean cell. Its impeller, machined from a single billet of aluminum, is balanced using high-speed spin balancers before being mounted to the planetary gear drive. The planetary gear unit, in turn, is gear-driven from the crankshaft and is fitted with helical-cut gears to reduce noise and increase torque handling. Once mated, the entire supercharger is tested in a closed-loop bench system, where it is spun up using a drive motor to simulate load and airflow output. Only if it meets the volumetric efficiency thresholds is it approved for installation onto the engine. As the supercharger is bolted onto the engine using a dedicated torque fixture, the entire power plant assembly is now ready to move to the dyno test cell. But before that happens, it's moved to a pre-test station where all fluids are filled. High-temperature synthetic oil, long-life coolant, and a special break-in fuel blend optimized for seating piston rings under load. The engine is then mounted into a test cradle wired with sensors and bolted to an eddy current dynamometer. Here, engineers run the engine through a programmed break-in cycle, gradually increasing load and RPM while monitoring combustion pressure, knock, oil pressure, and temperatures. Each engine must meet specific power output metrics before it's allowed to leave the test cell. For the H2R, this figure is over 310 horsepower, measured at the crankshaft. Engines falling short are automatically rejected and moved to a forensic diagnostics bench where engineers determine whether the issue lies in fuel delivery, boost pressure, valve timing, or internal mechanical components. Once the dyno-tested engine has passed all performance and durability checks, it is removed from the test cradle and placed onto a specially designed rolling engine dolly. This dolly is more than a simple transport mechanism. It interfaces with hydraulic lift systems allowing technicians to tilt, raise, and lower the engine precisely for the upcoming frame integration process. Before reaching the frame marriage station, however, the engine is routed through a pre-integration checkpoint where a technician conducts a final surface inspection, verifying all sealing surfaces, torque marks, and component connections. At this stage, all auxiliary components, such as the alternator, starter motor, oil cooler, and coolant hoses, are pre-mounted to reduce complexity during frame insertion. Meanwhile, the painted and fully inspected trellis frame, already cured and cooled from its powder coating process, is mounted on an assembly jig at the chassis preparation station. Here, the steering head bearings are greased and installed using an automated bearing press that ensures equal pressure distribution to avoid warping or damage. Into this steering head, the forged aluminum triple clamps are inserted and torqued to specification using a digital torque wrench with data logging capability. The handlebar mounts are temporarily attached for alignment purposes, but the handlebars themselves will come later in the line. At the engine marriage station, the prepped engine and trellis frame are brought together. A hydraulic lift slowly raises the engine into position beneath the frame, while two alignment pins guide the engine mounting points into perfect register with the frame brackets. 4 titanium bolts, lighter and stronger than traditional steel, are inserted and torqued in a diagonal sequence to avoid any stress concentrations. This step marks the true structural birth of the motorcycle. From this point onward, the machine is no longer a collection of parts. It is a unified mechanical system. With the engine mated to the frame, the motorcycle chassis is now placed onto the primary assembly line, an overhead conveyor system that moves each bike along a guided rail through multiple semi-automated workstations. The first station is the front suspension installation area. The H2R utilizes massive 43mm KYB AOS2 forks, which are fully adjustable and coated with a low-friction DLC layer. Each fork is filled with a precise volume of high-performance suspension oil using a vacuum fill station, then sealed and compressed to check for internal leaks. Once ready, the forks are inserted into the triple clamps and aligned using a digital laser alignment rig to ensure perfectly parallel orientation. Following this, the front wheel assembly, which consists of a Marchesini forged aluminum rim, dual 330mm Brembo discs, and a Pirelli slick racing tyre, is rolled up to the workstation. The wheel is mounted onto the axle, and the Brembo M50 monoblock calipers are installed with anti-vibration shims. The brake lines are routed along the fork legs using pre-formed clips, and each banjo bolt is torqued and marked with a color-coded paint pen for visual confirmation of completed steps. Parallel to the front suspension assembly, another robotic cell is preparing the swing arm sub-assembly. The H2R's single-sided swing arm is a hollow, forged aluminum unit with internal stiffeners. It is laser welded and then machined to accept the axle carrier and chain adjusters. Once verified for alignment using a 3D measurement gantry, the swing arm is connected to the frame using a solid pivot bolt, then connected to the rear shock. The rear suspension is a gas-charged KYB monoshock unit, also fully adjustable, and mounted on a rising rate linkage system for progressive damping under heavy loads. With front and rear suspension in place, the H2R is now a rolling chassis capable of supporting its own weight. At this point, the conveyor system gently lowers the motorcycle onto a rolling dolly with locking casters, freeing up the overhead rail for the next unit. The rolling chassis is pushed manually to the next station, the electronics and wiring harness integration bay. Unlike lower-tier motorcycles, where wiring is often installed as a single unified harness bundle, the H2R employs a modular wiring system. Multiple sub-harnesses for the engine control unit, traction control system, data logger, ABS system, and dashboard are installed independently, with each module having its own waterproof snap lock connector. The main harness is routed through the spine of the frame, secured with P-clips and thermal-resistant sleeves to protect from engine heat. Each connector is scanned using an RFID tool to ensure proper mating, and the system performs a low-voltage continuity check before proceeding. Once the electrical systems are routed, the control units are mounted in their designated locations. The inertial measurement unit is mounted beneath the seat. The ECU is housed in a vibration-isolated tray behind the headstock, and the quick shifter sensor is attached to the gear linkage rod. The dashboard, a full-color TFT display, is installed into the carbon fiber front cowl support and wired into the CAN bus network. With control systems in place, the next stage is the installation of the fuel system. The H2R's fuel tank is not merely a container, it is a shaped aluminum shell with internal baffles and foam inserts designed to reduce sloshing during extreme cornering. Each tank is pressure tested at 1.5 times normal operating pressure to check for leaks. A high-flow fuel pump is mounted internally, and the tank is lined with a corrosion-resistant coating that protects against ethanol degradation. The tank is installed onto rubber isolators on the frame spine and connected to the fuel rail via quick disconnect couplings. Underneath the fuel tank, the intake system comes together. The airbox is a sealed high-capacity plenum chamber designed to handle pressurized air from the supercharger. It features a ram air intake duct and a high-flow air filter made from synthetic fibers. Sensors for intake air temperature and pressure are inserted, and the throttle bodies, ride-by-wire, electronically controlled units, are bolted directly to the intake ports. The supercharger outlet feeds directly into the airbox, and a blow-off valve is installed to regulate excess pressure during throttle closure. Once all intake and fuel connections are secured, the exhaust system is installed. The H2R utilizes a titanium exhaust header that is hand-welded and purge-welded from multiple conical sections. Each pipe is flow bench tested prior to assembly to ensure even back pressure across all 4 cylinders. The exhaust system includes a collector and a short, undertail silencer, designed to reduce weight and maintain optimal power output with minimal restriction. Sensors for oxygen content and exhaust temperature are threaded into the headers and linked to the ECU. At this point, the bike is fully assembled mechanically, but bodywork has not yet been applied. That comes in the next segment of the production process. But before that, the motorcycle moves into the first startup and diagnostic bay. Here, technicians connect a master diagnostic tablet to the ECU via the OBD port. The system runs a full checklist, verifying sensor functionality, fuel pump pressure, throttle actuator operation, and system voltages. Once verified, the bike is started for the very first time. This initial start is a tense and critical moment. The technician listens closely for any abnormal mechanical noise, monitors the idle speed, checks for warning lights on the TFT display, and ensures that oil pressure rises immediately upon startup. The engine is allowed to idle until it reaches operating temperature, during which time the cooling fan, radiator circulation, and combustion balance are all evaluated. Any deviation from spec prompts an immediate stop and transfer to the diagnostic cell for further investigation. If the startup test is successful, the motorcycle is shut down and moved to the fluid leak test station. Here, a UV dye is added to the oil and coolant systems, and the bike is placed under black light to reveal any possible leaks at hoses, joints, or gaskets. Pressure is applied to the cooling system using a sealed radiator cap rig, and the oil system is pressurized via a pneumatic pump. This ensures that even micro leaks are detected before the bike proceeds to final cosmetic assembly. With all functional systems now tested and verified, the powertrain mounted, the electronics integrated, and the fluids checked for sealing integrity, the Kawasaki Ninja H2R is finally ready to receive what many consider its most striking feature, its full carbon fiber bodywork. Unlike plastic fairings found on standard motorcycles, the H2R's aerodynamic surfaces are crafted entirely from pre-preg carbon fiber panels that are formed, trimmed, and finished in a tightly controlled composites facility within Kawasaki's aerospace division. Each carbon panel, from the sculpted front cowl to the aggressive side fairings to the single-piece tail section, begins life as a sheet of carbon fiber impregnated with epoxy resin. These sheets are hand-laid into CNC machined aluminum molds, layer by layer, with careful attention to fiber orientation and overlap. This layup process determines the final strength and stiffness of the component. And technicians follow a digital blueprint showing precisely where each ply must be placed. Once the layup is complete, the mold is vacuum sealed inside a heat-resistant bag and placed into an autoclave. In the autoclave, the part is subjected to high temperature and pressure, curing the resin and fusing the carbon plies into a single monolithic shell. The process takes several hours, during which the exact pressure and thermal cycle are carefully controlled and logged. After curing, the mold is cooled and the part is demolded and sent to the trimming station. Here, 5-axis CNC water jet cutters remove excess material and create mounting holes, while laser measuring arms verify dimensional accuracy down to fractions of a millimeter. Once trimmed, each body panel goes through a polishing and surface inspection process. Technicians in cleanroom suits buff the surface to prepare it for paint, but for the H2R, this isn't just a cosmetic paint job. It's a defining visual signature. The entire carbon shell is sprayed with Kawasaki's proprietary mirror finish paint, a multi-layered formula that gives the H2R its iconic black chrome look. This paint contains a layer of silver-infused base coat that reflects light like a mirror, followed by multiple layers of clear coat that are wet sanded and polished between applications. The painted carbon fiber parts are then cured in low dust ovens at carefully controlled temperatures. When they emerge, they undergo final inspection under polarized lighting to reveal any imperfections invisible to the naked eye. Only when each piece passes this inspection are they released to the final cosmetic assembly line. Back in the main assembly hall, the rolling chassis is now stationed at the fairing installation bay. Here, a team of 2 technicians works on each unit, using soft-gloved hands and non-marring tools to install the carbon fiber bodywork. The upper cowl is mounted first, secured to a lightweight subframe using vibration-resistant fasteners. The side fairings follow next, installed with grommeted bolts and lined with thermal insulation on the inner surfaces to protect against engine heat. The winglets, a defining aerodynamic element of the H2R, are bolted to the sides of the front fairing using precision jigs. These carbon fiber strakes generate downforce at high speeds and are carefully aligned to match the factory's computational fluid dynamics models. The tail section, which includes the seat pan and integrated rear lights, is installed last. It slots over the subframe like a precision machined cover, secured with hidden fasteners that leave the outer surface clean and uninterrupted. The final visual pieces include the windscreen, made of high-impact acrylic formed over a heated vacuum mold, and the mirrors, which are unique to the H2R in that they are replaced by aerodynamic blades due to its track-only designation. These aerodynamic devices further contribute to the overall downforce and high-speed stability of the motorcycle. With all external components now in place, the motorcycle advances to the lighting and display verification stage. Even though the H2R is not street legal and lacks conventional headlamps, it still features essential lighting systems for track use, including brake lights and dashboard illumination. A diagnostic terminal is connected once more to the onboard electronics, which triggers all LEDs, signal displays, and digital readouts. Any pixel dropout or timing issue in the TFT display is immediately flagged, and the dashboard is swapped out before the motorcycle proceeds. The next phase is torque auditing. Using a handheld digital wrench interface, a technician rechecks every critical fastener on the motorcycle, referencing a torque database specific to the H2R. Each bolt, from the engine mounts to the suspension linkages to the brake calipers, is checked, and the data is wirelessly transmitted to a central quality control server. This system creates a complete torque audit trail for every unit, ensuring that no component is under or over-tightened, which could lead to safety issues under track loads. Following torque audit, the motorcycle is moved to the final mechanical verification bay, a rolling road dynamometer enclosed in a safety chamber. Unlike the earlier engine dyno test, this test evaluates the entire drivetrain system, including wheel alignment, chain tension, gearbox operation, and traction control responsiveness. The motorcycle is strapped down securely onto a rotating drum, and a technician rides the bike through a simulated series of track laps using paddle inputs to shift gears, apply throttle, and trigger braking. The onboard IMU and traction control system are monitored in real time to assess how the electronic aids respond under aggressive load transitions. One particularly crucial part of this test is the quick shifter evaluation. The H2R uses a bidirectional quick shifter that allows for clutchless upshifts and downshifts under load. The dyno software simulates various throttle and RPM combinations while the technician triggers shifts. Sensors measure delay time between shift input and gear engagement, and the ECU adjusts the ignition and fuel cut profile dynamically. If lag or false neutrals are detected, the quick shifter sensor or shift drum is re-inspected. Following dyno verification, the motorcycle is shut down and allowed to cool under controlled airflow. It is then cleaned using ionized air to remove any dust or debris collected during testing and rolled into the inspection corridor, a quiet, well-lit area reserved for aesthetic and dimensional verification. Here, trained inspectors examine every square centimeter of the motorcycle's surfaces under fixed angle lighting rigs that highlight reflections and contours. They check for paint consistency, panel fitment, fastener flushness, and emblem placement. The final inspection is concluded with a checklist signed by a master inspector who holds clearance to certify H2R units for packaging. A QR-coded certification tag is applied beneath the seat, containing digital records of every test, torque, spec, and visual check the motorcycle has passed. This tag remains with the bike for life, accessible by service centers and authorized Kawasaki technicians. At this point, the motorcycle is ready for crating and shipping, but before that occurs, a factory photographer captures high-resolution images of each unit for archival and legal purposes. These photos document the visual condition at the time of shipment and are stored alongside each VIN's production history. The H2R is then rolled into the final staging area, a climate-controlled packaging room where each motorcycle is carefully enclosed in a custom-built steel and wood crate. The front wheel is braced, the suspension compressed slightly with straps, and the bike is cocooned in protective foam. Every surface prone to scratching is wrapped with a low-tack film. Accompanying the motorcycle is a documentation pack that includes a certificate of authenticity, a technical user manual, a tuning guide, and the special tools required for trackside maintenance. Now ready for departure, the crated H2R is scanned into the logistics database and scheduled for dispatch. Its destination could be a private collector's garage, a professional racing team's paddock, or a high-end performance dealer specializing in exotic motorcycles. Once the Kawasaki Ninja H2R has been crated and logged into the factory's outbound inventory system, its journey through the global supply chain begins. The finished motorcycle, now nestled inside a reinforced steel-tubed crate, with engineered shock absorption inserts and padded contact points, is not treated like standard inventory. This is not mass market production. Each unit is registered and scheduled for delivery with the same level of care typically reserved for aerospace-grade cargo or high-value prototype machinery. The H2R crate is fitted with a tamper-evident seal and a GPS-enabled tracking unit. This small battery-powered device is embedded in the crate frame and continuously broadcasts location, temperature, and shock readings throughout the duration of the shipment. The goal is absolute transparency and control. Kawasaki's logistics division uses a centralized tracking portal to monitor every H2R in transit, ensuring that any anomaly, a sudden temperature spike, an excessive tilt angle during forklift handling, or an unexpected deviation from a scheduled route triggers a real-time alert and investigation. Within the Kawasaki factory's outbound logistics terminal, all outgoing H2Rs are staged in a secure area awaiting carrier pickup. This area is isolated from regular shipping docks and utilizes biometric access controls. When transport is scheduled, only certified freight handlers are permitted to load the crated bikes onto specialized trucks equipped with air ride suspension systems. These vehicles reduce vibration and road shock that could otherwise stress the precision-fitted carbon components or delicate electronics inside the crate. Each transport vehicle is assigned a specific destination hub, most commonly one of Kawasaki's global distribution centers. These hubs, located strategically in Europe, North America, the Middle East, and Asia, are more than just warehouses. They are hybrid facilities combining bonded customs zones, climate-controlled storage, and dealer preparation stations, all operating under strict quality assurance protocols. When a truckload of H2R units arrives at one of these hubs, the unloading process is supervised by Kawasaki regional logistics managers. Each crate is inspected for seal integrity and then scanned into the regional inventory management system using the embedded RFID and QR codes. For units destined for overseas markets, international freight forwarding is used. Crates are loaded into secure ISO shipping containers fitted with humidity control packs and shock-damping floor mounts. These containers are then booked onto cargo ships under insured, high-priority manifests. During ocean transit, the environmental monitoring systems embedded in the H2R crates continue logging data, which is uploaded via satellite uplink every 12 hours. When the containers reach port, customs clearance is expedited through Kawasaki's import-export licensing system, which pre-registers each motorcycle's VIN with the appropriate government authorities to simplify the paperwork associated with limited use non-street legal vehicles. Once the motorcycles arrive at their respective dealer prep centers, they are again moved using air ride trucks and secured holding bays. The dealer-level uncrating process is perhaps one of the most sensitive moments in the entire chain. These centers are equipped with padded flooring, overhead cranes, and specialized unboxing stations designed specifically for ultra-high performance motorcycles. Each crate is disassembled manually, using torque-limited tools to avoid overstressing any fastener. The protective wrap and foam buffers are removed, and a technician conducts a full visual inspection before any mechanical interaction occurs. At this point, the motorcycle is still in a semi-dormant state. While fully assembled at the factory, the H2R is shipped with several systems disabled or set to low activation mode. For example, the ECU is placed in a transport-safe state to prevent any unauthorized ignition or tampering during transit. The traction control system and launch control features are also disabled until activation codes are entered through the factory diagnostic tablet. These codes are provided only to certified Kawasaki race dealer technicians who have completed a specialized training program exclusive to the H2R platform. The first step during dealer prep is to activate the motorcycle's electrical systems. A lithium-ion high-output battery, which was shipped separately to avoid power drain or risk of damage, is installed using a torque-calibrated battery tray mount. The diagnostic tablet is then connected, and the technician runs a software handshake that reactivates the ECU, initiates a full sensor sweep, and calibrates the electronic throttle bodies to their neutral closed position. This is followed by a firmware update if required, ensuring that the bike is running the latest version of Kawasaki's proprietary control logic, an intricate blend of traction, wheelie, slide, and launch control algorithms designed for elite track use. Fuel is then added to the tank, typically a high-octane, ethanol-free race blend sourced by the dealer. This ensures consistent combustion characteristics for the first startup under the dealer's supervision. The cooling system is topped off with pre-mixed long-life coolant, and brake fluid levels are checked. While all systems were previously pressure tested at the factory, this step ensures that nothing has been compromised during transport. The first dealer-level ignition is performed under controlled conditions. The motorcycle is mounted on a paddock stand with wheel chocks and exhaust ventilation systems in place. The technician initiates the ignition cycle, monitors the startup process, and allows the bike to idle while all systems reach operating temperature. During this time, the technician observes engine temperature, oil pressure, throttle responsiveness, and warning indicators. Once warmed up, the throttle is blipped to ensure proper response from the supercharger system. A high-pitched whine confirms that the planetary gear-driven supercharger is spinning freely, and boost sensors are checked to verify pressure increase under transient throttle input. Next comes dynamic system calibration. The dealer technician enters a closed test loop menu via the diagnostic interface, and the motorcycle performs a series of controlled internal tests. These include throttle plate synchronization, IMU pitch and roll calibration, wheel speed sensor checks, and brake pressure modulation trials. These diagnostic steps ensure that all ride assist systems are correctly aligned and functioning before the motorcycle is released to the client. Before final delivery, cosmetic detailing is performed. The bike is cleaned using non-reactive anti-static cloths and waterless detailing sprays to preserve the mirror finish. Tire pressure is adjusted to the recommended range for track delivery, and chain slack is fine-tuned based on the factory's specification under rider weight simulation. The data logging module, if the customer has opted for the full telemetry package, is also installed at this stage, including its GPS antenna and onboard SD card reader. At this point, the motorcycle is ready for customer delivery, but the H2R is not simply rolled out onto the sales floor. In most cases, the delivery is either performed at a private unveiling event or within a dedicated performance showroom, often involving customer briefings, technical walkarounds, and personalized instruction. The purchaser receives a digital service log, a registration keycard for the diagnostic system, and, depending on region, a certificate of ownership detailing the motorcycle's serial number and place of manufacture. Some customers even receive a titanium plaque etched with their VIN, engraved at the factory using the same fiber optic laser that marks engine components. For customers intending to race the bike, additional services are offered. These include initial track setup, suspension tuning based on rider weight and intended circuit, and ECU mapping optimization. Kawasaki certified race engineers are sometimes deployed directly to high-profile clients to help integrate the bike into a team's racing fleet or private collection. In total, from the moment an H2R begins its life in the alloy preparation bay to the moment it is fired up in a client's garage or paddock, the process spans multiple continents, dozens of specialists, and a series of rigorously enforced quality checkpoints. No step is accidental. Every decision, from the type of crate to the orientation of the brake lines during shipping, is designed to protect and preserve the uncompromising nature of the Ninja H2R. The journey starts in Chevrolet's design and engineering departments, where teams of designers, mechanical engineers, and manufacturing planners work together to create not just the look of a vehicle, but the exact way it will be built. The earlier stages are dominated by design feasibility. Engineers ensure that the proposed vehicle shapes, curves, and mechanical layouts are compatible with large-scale manufacturing techniques. This includes determining how each body panel will be stamped, how wiring harnesses will be routed, and how components will be positioned for both performance and serviceability. It is here that design for assembly comes into play. In every element must be optimized for efficient installation without compromising quality or safety. This is especially critical for Chevrolet, which produces a wide range of models, from compact sedans to full-size trucks, each with very different manufacturing needs. Once the design is finalized, manufacturing engineering takes the blueprint and transforms it into a step-by-step factory plan. This involves defining which machines, robots, and tooling will be used at each stage of production, how workers will interact with them, and how the line will be sequenced to handle multiple model variations. Many Chevrolet plants are designed for mixed model production, meaning that a pickup truck and a crossover SUV could be assembled back-to-back on the same line. This requires extremely precise scheduling and tooling flexibility. The process begins with raw material arrival, particularly steel and aluminum sheets that form the vehicle's structural backbone. These materials arrive at the stamping plant in the form of enormous coils, each weighing many tons. The coils are unrolled, cut into blanks, and fed into massive stamping presses. These presses, some of the largest machines in the automotive world, shape the metal into fenders, roofs, doors, and other body panels using dies that weigh several tons themselves. Each panel typically goes through several stamping stages, moving from a rough shape to precise final contours. During stamping, dimensional accuracy is paramount. Even a fraction of a millimeter of error can cause alignment issues later in the build. Chevrolet uses automated inspection systems to verify each panel's geometry, rejecting or recycling any piece that fails to meet exact standards. This quality control in the stamping phase prevents costly rework later down the line. From stamping, the panels move into the body shop. Here, the flat, separate pieces are joined together to form the body in white, the term for the bare, unpainted vehicle shell. This process is dominated by robotic spot welding, where arms with welding guns move in perfectly choreographed sequences to fuse the panels together. The body shop operates on a combination of fixtures and jigs that hold each piece in precise alignment, ensuring structural strength and proper fit. The floor pan is laid down first, then side panels, roof structures, and reinforcements are added in a sequence determined by both structural integrity and manufacturing efficiency. Chevrolet plants use hundreds of welding robots, but human oversight remains critical. Skilled technicians monitor the welding cells, handle complex welds in tight spaces, and conduct random sample checks to confirm that weld penetration and positioning meet specifications. In some areas, adhesive bonding is used alongside welding to increase rigidity and reduce noise, vibration, and harshness. After the body is fully assembled, it undergoes detailed dimensional checks using coordinate measuring machines or laser scanning systems. If all is within tolerance, the body in white moves to the paint shop. The paint process is one of the most controlled environments in the factory, as even a speck of dust can mar the finish. The first step in painting is cleaning and pre-treatment. The body is submerged in a series of chemical baths to remove grease, oils, and contaminants. A phosphate coating is then applied to improve corrosion resistance. This is followed by the electrophoretic deposition, or E-coat, where the body is dipped in a charged primer bath that ensures complete coverage in every nook and cavity. The E-coat is then baked to cure it into a durable base layer. Once primed, the body passes through sanding and inspection areas before moving to the color base coat booths. Chevrolet's paint lines often use robotic spray arms programmed to follow complex paths that ensure an even application over curves, edges, and recessed areas. Some vehicles receive two-tone paint or special finishes, requiring masking and multiple spray cycles. The base coat is followed by a clear coat, which provides gloss and protection from UV rays and environmental wear. Each coat is baked in ovens to cure it, hardening the finish for durability. After the final paint cure, the body emerges looking complete on the outside, but it is still just a shell with no functional systems. This is where the trim and chassis assembly phases begin. The painted bodies move onto the trim line, where workers and robots install interior components in a carefully sequenced order. Wiring harnesses are routed through the body, HVAC ducting is fitted, and dashboards are installed as complete units. Seats, carpets, door panels, and center consoles are added, with quality checks at each station. Parallel to this, in another part of the plant, chassis sub-assemblies are being prepared. Engines, transmissions, front and rear suspension units, exhaust systems, and brake assemblies are mounted onto subframes. This pre-assembly ensures that when the time comes, the drivetrain can be installed into the body quickly and accurately. With the major mechanical and trim installations complete, the Chevrolet moves into the final assembly verification and testing phase. At this point, the vehicle is fully recognizable, but its systems have yet to prove themselves under controlled evaluation. This stage is where the factory shifts its focus from building to validating. One of the first stops is the wheel alignment station. Using laser-based or camera-guided systems, technicians check the alignment angles for each wheel: camber, caster, and toe. Proper alignment is essential not only for safe handling, but also for tire longevity and fuel efficiency. Adjustments are made at the suspension components until all readings are within Chevrolet's specified tolerances. These specifications are tied to each model's unique suspension geometry, ensuring consistent road feel across every unit. Next, the vehicle proceeds to the fluid fill and system pressurization stage. While many fluids, such as engine oil, brake fluid, and coolant have been partially filled earlier in the assembly process, this step ensures that all are topped off to exact levels and that the systems are free of leaks or trapped air. For braking systems, pressure testing and bleeding are performed to guarantee firm pedal feel and consistent stopping power. The fuel system is also pressurized and checked for leaks, as even minor seepage can create both safety and emissions compliance issues. Then comes one of the most exciting moments on the factory floor, the first engine start. At a dedicated startup station, the technician engages the ignition, bringing the Chevrolet's powertrain to life for the very first time. The engine's idle is monitored closely for smoothness, proper fuel-air mixture, and the absence of unusual noises or vibrations. The onboard diagnostic system is immediately scanned to ensure no fault codes are present. If a code does appear, it is addressed on the spot before the car moves on. After the initial start, the vehicle advances to the rolling road test, also known as the dynamometer station. Here, the car's drive wheels rest on large rollers that simulate real road resistance. A trained operator runs the vehicle through different speed ranges, gear changes, and acceleration profiles, while onboard sensors monitor performance. For automatic transmissions, shift smoothness is evaluated. For manual transmissions, clutch engagement and gear selection are tested. Braking performance is also checked under controlled simulated loads. This phase helps confirm that the powertrain, drivetrain, and braking systems are functioning exactly as intended before the vehicle ever touches pavement outside the plant. Following the rolling road, the vehicle undergoes an emissions and noise compliance check. In the emissions booth, Exhaust gases are captured and analyzed by high-precision equipment to ensure they meet the regulatory standards of the destination market. For noise compliance, sound level meters measure exterior and sometimes interior noise levels under specified conditions, ensuring that they fall within acceptable limits for both legal compliance and customer comfort. With these mechanical verifications complete, attention shifts to fine detailing and final adjustments. At the fit and finish inspection stations, experienced workers examine every panel gap, every seam, and every interior surface for perfection. Door alignment, hood closure effort, and trunk latch operation are all tested. Inside the cabin, all switches, controls, lighting, and infotainment functions are checked one by one. Even the alignment of stitching on seat upholstery can be grounds for rework if it fails to meet the brand's aesthetic standards. One of the more dramatic quality checks is the water leak test. The Chevrolet is driven into a sealed booth equipped with high-pressure spray nozzles that douse the vehicle from all directions, simulating heavy rainfall and road spray conditions. After several minutes, the vehicle is opened and inspected for any trace of water inside. Any leak, no matter how minor, is immediately repaired, often by replacing seals or adjusting window or door fitment. Once the car passes the water test, it proceeds to the underbody inspection area. Here, the vehicle is lifted and technicians check for proper routing of hoses, cables, and exhaust components. Protective coatings are examined to ensure full coverage, especially in corrosion-prone areas such as wheel wells and chassis rails. This stage is also a final safeguard for identifying loose fasteners or missing clips. The last stage before leaving the assembly building is the final audit. This is a comprehensive evaluation combining visual, functional, and performance checks into one ultimate sign-off process. The audit team often includes some of the most experienced personnel in the plant, and their approval is a requirement before a car can be released. Every system, from headlights to climate control, is tested again, and any deviation from perfect operation is corrected immediately. Once signed off, the Chevrolet is prepared for shipment. Protective plastic films are applied to painted surfaces most vulnerable to transit damage, such as hoods, roofs, and door edges. The interior is covered with disposable mats, seat covers, and steering wheel wraps to keep it pristine until delivery. From here, the vehicle enters the shipping yard, where it is grouped with others bound for the same distribution points. Domestic-bound vehicles are loaded onto specialized car carrier trucks with wheel straps securing them in place. For longer domestic routes, some are shipped by rail in enclosed auto racks. Export vehicles are driven onto roll-on/roll-off ships for overseas transport, where they are secured in dense, organized rows for the voyage. Upon arrival at regional distribution centers or directly at dealerships, each Chevrolet undergoes a pre-delivery inspection to ensure that transport has not caused any damage or alignment issues. Fluids and tire pressures are rechecked and protective coverings are removed. If accessories ordered by the customer were not installed at the factory, they may be fitted at this stage. Only after this chain of precise manufacturing, rigorous testing, and careful transport does the vehicle reach the customer. From the initial design to the moment the keys are handed over, every Chevrolet is the product of thousands of coordinated actions, each performed to uphold the brand's standards of reliability, performance, and quality. Long before a Hyundai rolls out of a showroom or cruises down a highway, it begins life in a complex and highly synchronized industrial process that blends advanced automation with skilled human craftsmanship. The journey starts far from the factory floor, in Hyundai's design and engineering centers, where teams of stylists, mechanical engineers, safety experts, and manufacturing specialists collaborate to transform a concept into a buildable reality. This early collaboration is critical. It ensures that the car's shape, structure, and systems are not only aesthetically pleasing and mechanically sound, but also feasible to mass produce. Every curve of the body is analysed for how it will be stamped from metal sheets. Every bracket and mounting point is evaluated for efficient installation, and every wiring harness route is mapped to avoid interference with other systems. Hyundai applies design for manufacture principles from the outset, reducing assembly complexity and ensuring consistent quality. Once the design is finalized, the manufacturing engineering teams take over. Their task is to translate that design into a precise, step-by-step production plan that integrates seamlessly into Hyundai's global manufacturing network. This means specifying which machines, robotic systems, and fixtures will be required, how the assembly line will be arranged, and what level of automation each task demands. Many Hyundai plants are set up for mixed model production, allowing sedans, SUVs, and even electric vehicles to be built on the same line. This flexibility demands exceptionally detailed scheduling and tooling strategies. The process physically begins with the arrival of raw materials. The backbone of most Hyundai vehicles is steel, often high strength, and sometimes blended with lightweight aluminum alloys for weight savings. These materials arrive in the form of massive coils, each weighing several tons, delivered by rail or truck directly to the stamping plant. Before the first press stroke, these coils are unrolled, cut into flat blanks, and fed into enormous stamping presses. These presses are monumental machines capable of exerting thousands of tons of force. They shape the flat metal sheets into body panels, such as fenders, roof sections, hoods, and door skins. Each panel typically passes through a series of dies, the first forming a rough shape, the following ones refining it to exact tolerances. Hyundai's dies are precision engineered and often swapped out by automated die changing systems to minimize downtime between production runs. Dimensional accuracy at this stage is essential. Even a slight misalignment in a stamped panel can cause compounding fitment problems later. To prevent this, Hyundai employs automated vision systems and laser scanners that inspect each panel as it leaves the press. Any panel outside specification is sent for recycling, with the metal returned to the supply chain to minimize waste. From stamping, the panels move into the body shop, a vast, robot-dominated hall where the skeletal structure of the car is assembled. Here, the flat pieces are transformed into the three-dimensional form of the vehicle in a process known as body-in-white assembly. This stage is dominated by robotic spot welding, with articulated arms, moving in carefully choreographed sequences to fuse panels together at hundreds of points. The process starts with the floor pan, onto which side frames, roof rails, and bulkheads are positioned and clamped into place by large jigs. These jigs ensure precise alignment so that every vehicle matches the dimensional blueprint exactly. Additional reinforcements are added at structural stress points, such as the pillars between the doors and the crash-absorbing sections at the front and rear. Although robots do the majority of welding, skilled human operators remain essential in the body shop. They handle welds in areas where robotic arms cannot easily reach, inspect the quality of robotic welds, and make fine adjustments to ensure panel gaps and alignment stay within tolerances. In some Hyundai models, structural adhesives are applied alongside welds to increase rigidity and reduce noise, vibration, and harshness in the finished car. Once the body shell is fully welded, it undergoes a dimensional inspection. This involves laser measurement systems or coordinate measuring machines that scan key reference points to ensure that the body conforms to the exact design specifications. Any deviation, even as small as a millimeter, can lead to problems fitting doors, glass, or interior components later. When the body passes inspection, it proceeds to the paint shop, one of the most meticulously controlled environments in the entire factory. The paint process is highly sensitive to dust, humidity, and temperature, so the paint shop is sealed and climate controlled. Before painting begins, the body is cleaned and pre-treated in a series of immersion baths. These remove oils from stamping and welding, apply a corrosion-resistant phosphate layer, and prepare the surface for primer adhesion. Following pre-treatment, the body is submerged in an electrically charged primer bath in a process called electrophoretic deposition, or e-coating. This ensures that primer reaches even hidden cavities, providing a uniform anti-corrosion layer. The body is then baked in an oven to cure the coating into a hard, protective shell. Next comes surface preparation. Technicians and automated sanding units smooth the primed surface, removing any tiny imperfections. The body then enters the base coat booths, where robotic arms apply the vehicle's chosen color in ultra-fine, even layers. For certain models, multi-coat or two-tone paint schemes require masking and additional spray cycles. After the base coat, a clear coat is applied to give gloss and long-term UV and chemical resistance. Each coating layer is cured in a controlled temperature oven to ensure hardness and durability. When the body emerges from the paint shop, it looks like a complete vehicle from the outside. But it is still just a shell. No drivetrain, no interior, and no wiring. This is when it moves to the trim and chassis assembly areas, where it truly begins to take on life. The first steps in trim assembly involve installing insulation and wiring. Sheets of sound-deadening material are placed strategically in the floor, doors, and bulkhead areas to reduce road and engine noise. Pre-assembled wiring harnesses are then routed through the vehicle, connecting future components such as lights, sensors, the infotainment system, and power accessories. These harnesses are secured with clips and ties to prevent rattles and wear over years of use. While the wiring is being installed, HVAC ducting and other hidden systems are fitted. Then comes the dashboard, which often arrives as a complete module from a supplier. Installing the dash is a delicate process, requiring alignment with mounting points and simultaneous connection of numerous wiring plugs. After the dashboard, seats are installed, bolted into the floor, and connected to their respective power or heating controls if equipped. Meanwhile, in a separate section of the plant, chassis and drivetrain components are being assembled into a single underbody module. This includes the engine, transmission, front and rear suspension units, exhaust system, and sometimes the steering assembly. Hyundai uses modular assembly techniques so that this entire unit can be brought to the body in one coordinated step. That step is known as the marriage, and it is one of the most visually striking moments on the assembly line. The painted body shell is suspended slightly above the moving chassis unit, and then the two are lowered and joined together. Bolts are torqued to precise specifications, linking the engine, drivetrain, and suspension to the body. Once the marriage is complete, fluid lines, electrical connections, and control linkages are secured between the body and chassis. This is followed by glazing, installing the front and rear windshields and side windows. High-strength adhesives bond the glass to the frame, contributing to both structural rigidity and weather sealing. By this stage, the Hyundai is a complete, self-contained unit, but it must undergo rigorous testing, adjustment, and final detailing before it is ready to leave the factory. With the body and chassis joined and the major mechanical systems in place, the Hyundai enters the final stages of production. A series of detailed inspections, dynamic tests, and finishing touches that ensure it meets both regulatory standards and Hyundai's own quality benchmarks. This part of the process is just as critical as stamping or welding because it determines whether the car will leave the factory flawless or require rework. The first stop is often the wheel alignment station. Using laser-guided or camera-based systems, technicians check the vehicle's suspension geometry, ensuring that the camber, caster, and toe of each wheel match precise factory specifications. Proper alignment not only affects handling and stability, but also determines tire wear and fuel efficiency. Adjustments are made by trained workers using specialized tools, often within a tolerance of a fraction of a degree. From alignment, the vehicle moves to fluid fill and system pressurization. Even though some fluids, such as engine oil or coolant, may have been partially filled earlier in the assembly, this stage ensures all systems are topped to exact levels. The brake and clutch systems are bled of any trapped air, guaranteeing consistent pedal feel. The air conditioning system is charged with refrigerant, and the fuel system is pressurized to check for leaks. In hybrid or electric models, the high voltage battery systems are also energized and checked for correct function. One of the most significant milestones comes next: the first engine start. At a dedicated station, a technician initiates the ignition sequence or engages the start button. The powertrain roars or hums to life for the very first time. While this moment has a certain ceremonial feel, it is primarily a diagnostic test. Sensors and the onboard diagnostic system are immediately scanned for error codes, while technicians listen for any abnormal sounds and monitor idle stability. Any fault detected is addressed immediately before the car progresses. Following the initial start, the Hyundai is driven onto a rolling road dynamometer, a sophisticated test rig with large rollers beneath the wheels. Here, the vehicle's drivetrain is run through a series of simulated driving conditions. Technicians shift through gears, accelerate, decelerate, and brake, all while sensors record performance metrics. This test checks everything from transmission shift quality to ABS functionality. For electric and hybrid vehicles, regenerative braking performance is also verified. The dynamometer can simulate different road loads, allowing Hyundai to ensure the vehicle responds correctly in both light and heavy driving scenarios. Next, the vehicle enters an emissions and noise compliance station. The exhaust system is connected to high-precision analyzers that measure levels of pollutants such as carbon monoxide, hydrocarbons, and nitrogen oxides, ensuring compliance with the environmental regulations of the target market. Noise testing is also performed, measuring sound levels both outside and sometimes inside the cabin to confirm they meet legal and brand comfort standards. Once mechanical and emissions checks are complete, the Hyundai proceeds to the fit and finish inspection area. This is a zone where highly trained quality inspectors meticulously examine the car's exterior and interior for even the smallest imperfections. Panel gaps are measured with gauges, paint surfaces are inspected under bright, angled lighting to reveal any blemishes, and all interior features are tested for correct operation. If a trim piece is misaligned by even a millimeter, it is corrected on the spot. One of the most important tests at this stage is the water leak test. The car is driven into a sealed chamber fitted with high-pressure spray nozzles, which bombard it with water from all angles to simulate heavy rainfall and road spray. After several minutes, technicians open the doors, trunk, and hood to inspect for any signs of moisture inside. Leaks are unacceptable, so any that are found trigger immediate sealing repairs or component adjustments. Underbody inspection follows, with the vehicle lifted on a hoist so workers can check that exhaust systems, fuel lines, brake hoses, and electrical cables are correctly routed and securely fastened. Protective coatings applied earlier in the build are examined for complete coverage, especially in high corrosion areas like wheel wells and chassis cross members. The final audit is the last checkpoint before a Hyundai can be cleared for shipment. This audit is a condensed but highly rigorous version of all prior tests. Inspectors cycle through every electrical control, verify all lighting and warning systems, and ensure the climate control works in heating and cooling modes. They also test locking systems, window regulators, mirrors, infotainment units, and safety features like airbags through diagnostic systems. The goal is to confirm that the car leaving the factory is indistinguishable in quality from any other unit of the same model, regardless of production date. Once the final audit is passed, the car moves to the shipping preparation area. Protective films are applied to vulnerable painted surfaces, such as the hood, roof, and trunk lid, to guard against minor scratches or debris during transport. Interior surfaces, such as seats and steering wheels, are wrapped with disposable covers. The vehicles are then driven to the factory's dispatch yard, a vast parking area organized by destination. Here, they are scanned into Hyundai's logistics system using their unique vehicle identification numbers. This tracking system links each car to its market, dealer, and production details. Domestic shipments are typically loaded onto multi-deck car carrier trucks, secured with wheel straps to prevent movement. For longer domestic journeys, rail transport in enclosed auto racks may be used. Vehicles bound for export markets are moved to ports, where they are driven onto roll-on/roll-off ships. These massive vessels function like floating parking garages, with cars parked in tight formation and secured for the ocean voyage. Once at their destination country, the vehicles undergo customs clearance before heading to Hyundai's regional distribution centers. Here, a process called pre-delivery inspection, or PDI, is performed. This includes removing protective coverings, checking fluid levels and tire pressures, and confirming no damage occurred during transport. Any market-specific adjustments, such as headlight alignment or software settings, are made at this stage. From the distribution center, the cars are delivered to dealerships, where a final light inspection is carried out before they are placed on display or prepared for customer delivery. When the new owner takes the keys, the journey that began with raw steel coils and a concept drawing is complete. Though for Hyundai, the feedback loop from customer to factory continues, helping refine the next generation of vehicles. Before a Nissan vehicle ever reaches the open road, its story begins long before the first bolt is tightened or the first panel is painted. The creation of a Nissan car is a journey that blends advanced engineering, precision manufacturing, and human skill into a seamless, highly coordinated process. It begins in design studios and engineering departments, where the model is conceived, refined, and optimized for production. Design is never just about looks. For Nissan, every curve and contour is evaluated for aerodynamic efficiency, structural integrity, and manufacturability. Engineers work closely with manufacturing planners to ensure that the design can be built consistently at high volume. This process is called design for manufacturability, and it addresses questions like, can a panel be stamped without deforming? Can a wiring harness be installed without excessive labor time? Can a structural weld be made easily by a robot? These early decisions will determine the efficiency and quality of the factory floor operations months or even years later. Once the design is finalized, manufacturing engineering takes over. This is where the factory plan is built, specifying the sequence of operations, the type of machinery to be used, and the layout of the assembly line. Nissan's factories are often capable of building multiple models on the same line, which means the plan must account for mixed model production. In practice, this requires flexible tooling, quick change robotic programs, and precisely timed deliveries of parts so that the right components are always at the right station when a specific model arrives. The physical process starts with the arrival of raw materials, primarily steel and aluminum. These materials, often in the form of giant coils weighing several tons, are delivered by rail or truck to the plant's stamping facility. Before a single press stroke is made, the coils are unrolled, flattened, and cut into blanks, flat sheets of the correct size for the parts to be made. These blanks are then fed into huge stamping presses capable of exerting thousands of tons of force. Each body panel, whether it's a door skin, roof panel, fender, or hood, is formed by passing through several stages of dies. The first die forms the rough shape. while subsequent dies refine the panel, adding curves, ridges, and precise dimensions. The dies themselves are precision-engineered steel blocks that must be perfectly aligned and maintained to avoid defects. Quality checks start here. Robotic measuring arms or laser scanners inspect the panels for dimensional accuracy and surface quality. Even minor ripples or distortions can cause problems later during assembly, so any out-of-spec panels are removed from the line and sent for recycling. From stamping, the panels are moved into the body shop, a large, highly automated hall where the panels are welded together to form what is known as the body in white. This is the skeletal shell of the car before painting and assembly. Large jigs and fixtures hold panels in the exact position while robotic arms perform spot welds, fusing the metal together. In modern Nissan plants, robots handle the majority of welds, ensuring speed, repeatability, and strength. The process usually starts with the floor pan. Side panels, roof structures, and cross members are added in a carefully planned sequence to maximize rigidity and precision. Reinforcements for crash safety, such as high-strength steel beams in the doors and roof pillars, are installed at this stage. Doors may be temporarily hung for alignment checks, but are often removed later to make interior assembly easier. Although automation dominates, human workers remain essential. Some welds, especially in tight or complex areas, are better handled by skilled technicians. Workers also monitor the robotic systems, making adjustments when necessary and performing visual checks for weld integrity. When the body shell is complete, it undergoes a dimensional inspection using coordinate measuring machines or laser scanning systems. This ensures that the structure matches the precise dimensions required for later assembly steps, where mismatches can cause issues with panel fit or sealing. Next, the bare metal body heads to the paint shop, an area of the factory with the most stringent cleanliness requirements. Dust, dirt, and moisture can ruin a finish, so the paint shop is a sealed, climate-controlled environment. Before painting, the body goes through a series of pre-treatment baths to remove any residual oil or dirt from stamping and welding. These baths also apply a phosphate layer that improves corrosion resistance. After pre-treatment, the body undergoes electrophoretic deposition, or e-coating. In this process, the body is submerged in a primer bath where an electric charge causes the primer particles to bond evenly to the entire surface, including hidden cavities and seams. The coated body is then baked in an oven to cure the primer into a hard, protective layer. Once cured, the body is sanded to smooth the surface before the color coats are applied. Robotic sprayers, precisely programmed for each model and color, apply the base coat evenly over every contour. In some cases, human painters handle special finishes or complex two-tone applications. After the base coat, a clear coat is applied to provide gloss and protect against UV and environmental damage. Each coat is cured in an oven, hardening the finish and locking in the color. When the painted body emerges, it looks complete on the outside, but remains an empty shell. The next stage, trim and chassis assembly, is where the car starts to take shape as a functional vehicle. The first step in trim is installing sound deadening materials, insulation, and wiring harnesses. These harnesses, pre-assembled into model-specific layouts, are routed through the body and secured in place. HVAC ducting is fitted, followed by the dashboard, which usually arrives as a fully assembled unit from a supplier. Seats are bolted into place, carpet is laid, and door panels are installed. In parallel, the plant's chassis line is assembling the mechanical heart of the car. The engine, transmission, suspension assemblies, exhaust system, and brakes are mounted onto a subframe or separate underbody unit. This modular approach allows for rapid final assembly once the chassis and body are ready to be joined. The marriage process is one of the most striking moments in Nissan's assembly line. The painted body is suspended above the rolling chassis module, and the two are brought together by synchronized lifts. Bolts are torqued to specification, connecting the drivetrain and suspension to the body. Following the marriage, technicians connect the various systems between body and chassis, electrical plugs, coolant hoses, fuel lines, steering linkages, and more. Windows are installed using high-strength adhesive, and exterior trim pieces such as weather strips, moldings, and badges are applied. At this point, the Nissan is a complete vehicle in form, but must still prove itself in function. The next phase, testing, inspection, and final adjustments, will determine whether it is ready for shipment to customers. With the major assembly work finished and the Nissan now standing as a complete vehicle, the factory's focus shifts toward verification, fine-tuning, and preparing it for the journey beyond the plant gates. This stage is not simply a final glance over the product. It is a comprehensive series of tests and inspections designed to ensure that every function operates exactly as intended and that the vehicle meets Nissan's rigorous quality standards as well as the legal requirements of its destination market. The first stop in this phase is usually the wheel alignment station. Here, precision laser or camera-based measurement systems determine the exact angles of each wheel relative to the chassis. Technicians adjust camber, caster, and toe to within factory specifications. A misalignment at this stage would not only affect handling and tire life, but could also cause warranty claims, so the process is handled with meticulous care. From there, the vehicle moves to the fluid fill and pressurization stage. While some fluids such as oil and coolant may have been partially filled earlier, this step ensures that all systems are fully charged to their specified capacities. Brake and clutch hydraulics are bled to remove any trapped air, guaranteeing a firm pedal feel. Air conditioning systems are charged with refrigerant, the fuel system is primed, and in hybrid or electric models, high voltage battery systems are energized and checked for correct operation. Each fill station uses automated metering systems to deliver exact volumes, minimizing waste and ensuring repeatability. One of the most anticipated moments comes next, the first engine start. At a dedicated station, the technician engages the ignition or push button start, bringing the Nissan's powertrain to life for the very first time. While this might appear ceremonial, it is primarily a diagnostic event. The vehicle's onboard computer is scanned for any fault codes, idle speed is observed, and technicians listen closely for any unusual noises or vibrations. If a warning light appears or a diagnostic scan reveals an error, the vehicle is diverted to a repair bay before continuing. Once the initial startup checks are complete, the Nissan moves to the rolling road, also called the chassis dynamometer. Here, the drive wheels rest on large rollers that simulate road resistance. A trained operator runs the vehicle through various speeds, load conditions, and gear changes, while onboard sensors and external instruments record performance. This stage verifies smooth transmission shifts, proper acceleration response, correct ABS function, and stability control operation. For electric and hybrid models, regenerative braking efficiency is also tested. Following the dynamic test, the vehicle enters the emissions and noise measurement booth. Exhaust gases are captured and analyzed to ensure compliance with the emissions regulations of the market the car is destined for, whether that's Europe, North America, or Asia. The booth may also include sound level monitoring to verify that engine and exhaust noise remain within acceptable limits. For some models, interior noise levels are also measured to maintain Nissan's comfort standards. With the drivetrain and emissions verified, the Nissan proceeds to the fit and finish inspection zone. This is a brightly lit area where experienced inspectors examine every exterior panel and interior surface. Panel gaps are measured to ensure uniformity, and paint is checked under angled lighting that reveals imperfections invisible in normal conditions. Inside, every control, switch, and display is operated to confirm proper function. HVAC systems are tested for both heating and cooling performance, infotainment units are powered on, and tested for audio quality, and safety features, such as seatbelt warning systems, are checked. One of the most critical functional tests is the water leak check. The car is driven into a sealed chamber fitted with high-pressure water nozzles that bombard it from all directions, simulating heavy rain or car wash conditions. After several minutes of soaking, technicians enter the vehicle to check for even the slightest signs of moisture. Any leak detected, whether from a window seal, door gasket, or body seam, results in immediate repair and retesting. Next comes the underbody inspection. The vehicle is lifted on a hoist so workers can examine fuel lines, brake hoses, exhaust components, and electrical wiring for correct routing and secure fastening. Protective coatings applied earlier in the build are checked to ensure they fully cover vulnerable areas, especially in regions prone to corrosion. This step also allows for one last visual confirmation that no tools, fasteners, or foreign objects have been left behind during assembly. The last in-plant checkpoint is the final audit. This is a comprehensive, multi-point inspection that serves as the ultimate quality gate before the vehicle is released for shipping. The audit team includes some of the most experienced inspectors in the plant, and their role is to verify that every system operates flawlessly. The process includes both static checks, such as lights, controls, and displays, and short, low-speed driving within the factory grounds to confirm steering feel, brake performance, and noise levels. When a Nissan passes the final audit, it is cleared for shipment. In the shipping preparation area, protective films are applied to painted surfaces most likely to be scuffed during transport, such as the hood, roof, and door edges. Interior surfaces like the seats, steering wheel, and carpets are wrapped with disposable covers. The cars are then driven to the factory's dispatch yard, where they are parked in organized rows according to their destination. Each vehicle is scanned into Nissan's logistics system using its unique vehicle identification number, linking it to production data, quality records, and shipping instructions. Domestic-bound cars are usually loaded onto multi-level car carrier trucks, with each vehicle secured using wheel straps or chocks to prevent movement. For longer inland journeys, rail transport in enclosed auto racks is sometimes used. Export vehicles are driven onto roll-on/roll-off ships, enormous vessels designed specifically for transporting thousands of cars at once. Inside the ship, the vehicles are parked in tight formation and secured with lashings to keep them stable during ocean crossings. When the ship reaches its destination port, Nissan vehicles are driven off and placed into secure holding areas for customs clearance. Once cleared, they are transported to regional distribution centers. Here, a process called pre-delivery inspection, or PDI, is carried out. Technicians remove transport protections, recheck fluids and tire pressures, confirm there is no transport-related damage, and make any market-specific adjustments, such as software updates or headlight aim changes. Finally, the vehicles are dispatched to dealerships, where a last brief inspection is done before placing them on the showroom floor or preparing them for immediate delivery to customers. The moment a buyer takes the keys marks the end of the manufacturing journey, but for Nissan, the process is part of a continuous loop. Feedback from customers and dealerships feeds back to engineering and manufacturing teams, influencing improvements for future models. The highlight of this stage is the marriage, when the body is lowered onto the chassis assembly. Using synchronized lifts, the two halves are brought together, and fasteners are torqued to precise specifications. At this point, the Chevrolet vehicle has its structural and mechanical systems fully united. From here, connections are made between the body and chassis systems. Electrical hookups, fluid lines, control linkages, and exhaust mounts are all secured. Windows are bonded into place with high-strength adhesives exterior trim and badging are applied, and final adjustments are made to doors, hoods, and trunk lids to ensure perfect fit and operation. The story of the Land Cruiser's creation begins long before the first bolt is fastened or the first body panel is stamped. It starts with design intent, precise engineering blueprints, and a commitment to quality control that informs every choice along the production line. Before even a single part enters the assembly plant, Toyota engineers have spent years developing the latest Land Cruiser model, using computer-aided design systems, crash simulation software, and off-road test labs to validate every frame weld, axle articulation angle, and suspension rebound setting. These simulations and pre-manufacture analyses create the digital foundation upon which the physical vehicle will be built. Now, when we arrive at the factory, typically one of Toyota's dedicated SUV production plants, such as the Tahara or Yoshiwara plant in Japan, we're greeted not by the roar of chaos, but by a carefully orchestrated ballet of steel, robotics, and human oversight. This factory is more than a collection of machines. It's a living system, optimized for repeatability, efficiency, and above all, zero-defect manufacturing. The first physical component of the Land Cruiser to be created is the frame. Unlike unibody vehicles that integrate body and frame into one structure, the Land Cruiser is built using a full ladder frame chassis, a hallmark of serious off-roaders and heavy-duty trucks. This ladder frame starts its life as a series of precisely cut and formed steel sections, each made from high-strength, hot-rolled steel that arrives at the plant in massive coils. These steel coils are unrolled and fed into CNC-controlled stamping and cutting machines that shear the metal into the required dimensions for the side rails, cross members, and mounting brackets. Once these components are formed, they move to the frame welding station. Here, an array of industrial welding robots, suspended from gantries and articulated arms, descend upon jigs that hold each piece in place with sub-millimeter precision. These jigs are crucial. They ensure that each frame is square, symmetrical, and dimensionally accurate to fractions of a millimeter. Using MIG and MAG welding techniques, the robots trace complex bead paths, fusing the frame together with a consistency that only automated systems can deliver. After each frame is welded, it undergoes dimensional scanning using laser measuring systems, which compare the physical result against digital blueprints in real time. Any variance is flagged immediately and either corrected or discarded, depending on severity. From here, the raw frame undergoes an extensive surface preparation process. It is conveyed through an immersion tank line where it's degreased, cleaned, and dipped in an anti-corrosion phosphate coating. This is followed by a cathodic electrodeposition primer bath, commonly known as e-coating, where an electrical current bonds anti-rust primer to every exposed surface of the frame, even inside enclosed box sections. Once coated, the frame is baked in a curing oven to harden the primer layer, forming the first shield against corrosion that the Land Cruiser will face in its lifetime. Meanwhile, in a parallel part of the factory, body components are being fabricated. These include the outer shell, roof panels, doors, hoods, and tailgates. Each component is stamped from galvanized steel sheets using a massive press line. These presses exert thousands of tons of force to transform flat metal sheets into complex, three-dimensional shapes in just seconds. Every panel must emerge with zero warping, perfect contours, and clean edges. Here again, quality control is relentless. Vision systems scan each panel for wrinkles, cracks, or inconsistent radii. These individual panels are then conveyed to the body shop, where robotic arms perform spot welding to assemble them into what's called the body in white, a complete, unpainted car body without any moving parts. Unlike the frame, which is welded largely by robots, the body in white assembly involves a mix of automation and skilled manual welding, particularly in complex joint areas where human adaptability still outperforms machines. Workers in specialized welding suits and helmets double-check robotic welds, perform precise manual tacks, and insert structural adhesives that bond key stress points for added torsional rigidity. Once both the ladder frame and body in white are complete, they proceed along separate lines toward eventual integration, but not before the body receives its finish. This takes place in the paint shop, a fully enclosed and environmentally controlled section of the plant where air filtration, humidity, and temperature are all tightly regulated. The body is first cleaned in a multi-stage wash tunnel, then passes through a second E-coat dip tank, identical in principle to the one used for the frame. After curing, the body moves through a sanding and inspection stage where workers dressed in white lab-like uniforms hand sand each panel to create a flawless surface for painting. Next comes the paint booth. Here, electrostatic spray robots apply multiple layers of base coat and clear coat, often in high-end two-tone or metallic finishes. These robots mimic human movement with incredible dexterity, able to reach deep crevices while maintaining a uniform paint thickness. Between coats, the body passes through baking ovens to cure each layer, producing a deep, resilient finish that can withstand the harshest climates, whether desert, jungle, or tundra. As the body is being painted, attention shifts to the powertrain assembly line. The Land Cruiser's engine is a marvel of durability engineering, often a turbocharged V6 or robust, naturally aspirated V8, depending on the model year and market. These engines are assembled in a dedicated engine plant, either nearby or in a regional facility. Engine blocks are cast from aluminum or iron alloys, then machined with extreme precision to form cylinders, crankshaft seats, and oil galleries. Assembly teams install pistons, crankshafts, camshafts, timing systems, and cylinder heads, each torqued and timed to tight tolerances. Every engine is then hot tested using a dynamometer, simulating real-world loads to verify compression, torque, emissions, and idle behavior. Once validated, the engines are sent to the main vehicle assembly plant, where they await union with the transmission, either a rugged automatic gearbox or a manual transmission for certain utility models. These are coupled to the engine via robotic clutch alignment and torque checking machines, ensuring concentric balance and zero runout. The completed powertrain is then lowered onto a moving subframe, which also includes the front and rear differentials, transfer case, and drive shafts. At this point, we reach one of the most iconic moments in Land Cruiser production, the marriage process. This is when the body and frame finally come together. The fully painted body in white is carefully lowered onto the rolling chassis by a massive overhead gantry system. Workers align frame mounts with precision machined body bushings and use pneumatic tools to torque heavy-duty bolts to exact specifications. This moment is both symbolic and practical. It's the point at which the Land Cruiser becomes more than a collection of parts. It becomes a single, cohesive machine. With the body now secured to the ladder frame chassis, the Land Cruiser has taken on its distinctive silhouette, but it remains little more than a shell with a skeleton. To bring this vehicle to life, the next phase involves the precise installation of its drivetrain, suspension, and electrical nervous system, a process that combines brute mechanical assembly with intricate wiring, calibration, and testing, all executed on a constantly moving assembly line. Once the marriage process is complete, the vehicle is conveyed via automated guided carriers to the suspension installation zone. Here, factory technicians install the front and rear suspension assemblies onto the mounting points integrated into both the chassis and subframe. The Land Cruiser, unlike crossover SUVs, is designed for real-world abuse and off-road articulation, so its suspension is often built around independent double wishbone geometry in the front and a multi-link solid axle or live axle setup in the rear, depending on the variant. The suspension components arrive as pre-assembled modules: control arms, coil springs or air suspension bags, dampers, stabilizer bars, and mounting bushings, all staged in precise sequence. Using robotic torque arms and hydraulic lifts, technicians align and fasten each assembly to the vehicle's mounting brackets. Torque settings are tightly controlled and digitally monitored using torque sensing tools that immediately signal if any fastener is under or over tightened. This is especially critical on a vehicle like the Land Cruiser, where off-road stress loads can be severe, and even the smallest flaw could lead to long-term durability issues. Following suspension installation, the axles and drive shafts are connected. These link the differentials, already installed on the frame during powertrain sub-assembly, to the wheel hubs. Front and rear prop shafts are aligned and bolted to their respective flanges using flexible couplings that allow articulation without transmitting vibration into the chassis. The transfer case, which enables the vehicle's four-wheel drive capabilities, is now electronically linked to the vehicle control system using waterproof harnesses, which are clipped into place along the underbody routing channels. In the adjacent station, the brake system comes to life. Calipers, brake discs, hydraulic lines, and ABS wheel sensors are pre-installed on knuckle assemblies and now joined to the master cylinder and vacuum booster at the front of the vehicle. Every brake line is fitted using anti-corrosion coated clips and rubber grommets that isolate vibrations and prevent wear. After installation, the brake system is filled with fluid using an automated vacuum fill machine that ensures the lines are completely purged of air, critical for consistent pedal feel and braking performance. Sensors verify fluid pressure and pedal actuation force during a quick bench test before the vehicle moves on. As the mechanicals begin to solidify, another equally vital process unfolds in parallel: the installation of the vehicle's wiring harnesses and onboard electronics. Modern Land Cruisers have extensive electrical systems, covering everything from engine management and safety systems to multimedia interfaces and off-road terrain response modules. The primary wiring harness is a massive, branching structure composed of thousands of color-coded wires bundled by function and destination. This harness is laid manually into the body shell by trained technicians who follow a strict sequence and routing path. Each connection is marked by a QR code or barcode that technicians scan to verify proper fit and location. The harnesses are clipped into custom-molded plastic retainers, and junction boxes are secured in the engine bay, cabin, and underfloor areas. Grounding points are torqued to chassis connections, and fuse boxes are populated with model-specific fuses and relays. By this stage, the Land Cruiser's central nervous system is beginning to form, ready to carry data, commands, and electrical current to every corner of the vehicle. Next comes the fuel system. A large, impact-resistant polymer fuel tank is mounted under the rear chassis rails using steel straps and dampers. This tank has internal baffles to prevent sloshing and is equipped with level sensors, pressure regulators, and a high-flow electric fuel pump. Once installed, quick connect fuel lines are clipped to the underbody routing paths and connected to the engine's fuel rail, with multiple pressure checks verifying that the system is sealed and ready for operation. At this point in the line, attention shifts to the interior, an area where Toyota applies as much precision as it does to mechanical systems. The bare cabin, still painted but unadorned, now receives layers of insulation, padding, and trim components. Sound deadening mats are applied to the floor pan using heat-activated adhesive rollers, followed by thermal insulation sheets placed along the firewall and under the roofline. These materials are crucial in creating the Land Cruiser's signature interior quietness, especially in rugged environments. Once the insulation is laid, flooring components such as the carpet, footwell liners, and underseat padding are installed. Technicians then mount the dashboard assembly, an enormous, complex component pre-built at a substation with integrated wiring, HVAC vents, infotainment screens, and control buttons. The dashboard is robotically guided into position and bolted to the firewall using multi-axis torque arms, ensuring a perfect alignment with side panels and center console structures. The steering column is next. It includes electric tilt and telescoping motors, a collapsible shaft for crash safety, and electronic interfaces for steering angle sensors and driver assistance systems. It's fitted from below and torqued to both the firewall and dash crossbar. Following this, the front seats are wheeled in on trolleys and installed using locator pins and power connectors that automatically link heating, cooling, and adjustment motors into the body harness. Rear seats, cargo trim, door cards, and overhead components follow, each snapped and bolted into place with pre-assembled clips and hardware. Moving further down the line, the door assemblies, painted, glazed, and pre-trimmed in an earlier stage, are now mated to the body. Large articulated robots or specially designed lift assist rigs help align the heavy doors to their hinges. Once bolted into place, technicians adjust each door for flush fitment using feeler gauges and laser guides to ensure panel gaps are within tolerance. Power window motors and locks are connected and tested in real time. At this point, exterior fittings begin. The front grille, headlights, taillights, bumpers, and fender flares are installed. The Land Cruiser's lighting system is particularly complex, involving adaptive LED arrays, daytime running lights, and integrated washers for certain models. Each component is wired, clipped, and sealed with weatherproof gaskets to ensure long-term durability in wet or dusty environments. Sensors for parking assist, radar cruise control, and blind spot monitoring are installed behind trim panels, with calibration to follow in later stages. The wheels and tires, often rugged, all-terrain types with reinforced sidewalls, are mounted next. These are torqued using automatic nut runners that measure clamping force electronically. Wheel alignment is then performed using an advanced, laser-guided system that adjusts toe, camber, and caster values to factory specifications. This step ensures the Land Cruiser will track straight and true from the first meter of use. Now, with a fully assembled interior, powertrain, suspension, and exterior, the Land Cruiser reaches the electrical testing and fluid fill stations. Here, every onboard system is powered up and scanned using a diagnostic tool plugged into the vehicle's onboard data port. Over 150 sensors and modules are queried for error codes. Air conditioning is filled with refrigerant. The power steering, coolant, transmission, and differential oils are pumped into their respective reservoirs via closed-loop filling systems that eliminate contamination. Each fluid fill line has inline flow meters, digital volume counters, and pressure regulators to ensure precise volumes are administered, with system pressure monitored for anomalies. Technicians conduct function tests on HVAC controls, infotainment systems, dashboard illumination, reverse cameras, and audio systems. Even the seat memory buttons are activated to verify motor control and data retention. As the Land Cruiser nears final assembly, it undergoes a simulated ignition. The engine is started for the first time, and technicians listen for abnormal vibrations, rattles, or leaks. Exhaust gas sensors verify emission compliance, and drive-by-wire throttle response is tested under load. The vehicle is driven onto a rolling road dynamometer where automated systems simulate various road conditions to test acceleration, braking, and driveline engagement. With the mechanical assembly now complete and the engine having roared to life for the first time, the Land Cruiser enters a critical phase of its production journey: quality validation and final inspection. At this point, every system is functional, but the factory's role is not merely to assemble parts. It is to confirm that each individual Land Cruiser meets Toyota's legendary standards of durability, safety, and refinement. This is where precision testing, calibration, and simulation converge to ensure that not a single flaw escapes into the real world. The vehicle first proceeds to the final inspection conveyor, a slow-moving belt surrounded by inspection bays and quality control technicians. Here, the vehicle is subjected to a comprehensive visual and tactile inspection. Under bright, uniform lighting conditions and mirrored surfaces designed to expose even the slightest ripple or scratch, skilled workers scan the painted body panels for cosmetic perfection. They run gloved hands over each surface, checking for texture inconsistencies, orange peel effects, or trapped particles under the clear coat. Special attention is paid to panel gaps and alignment. Each door, hood, and tailgate is opened and closed repeatedly to ensure smooth operation and consistent shut lines. A precision feeler gauge is used to measure the distance between adjacent panels at multiple points, confirming that they fall within Toyota's strict tolerances, often less than 3 mm in variance. Any deviation triggers a corrective rework, often involving panel realignment or trim replacement. Inside the cabin, technicians perform a fit and finish audit, systematically checking every touchpoint, seam, and surface. They press every button and knob, ensuring proper tactile feedback and response. Seat adjustments, steering wheel tilt and telescoping, mirror positioning, and window operation are verified. Even cabin lighting is checked, not just for function, but for uniformity in color temperature and intensity. Every HVAC vent is opened and closed. Cup holders are tested for resistance and rattle, and storage compartments are opened to confirm smooth latching and retention. Next, the Land Cruiser undergoes a leak and weatherproofing test in what's known as the shower booth or rain simulation chamber. This sealed room replicates an intense downpour, up to 50 litres of water per square metre per minute for several minutes, while the vehicle remains stationary. High-pressure nozzles blast water at strategic angles, covering the windshield, roof, door seals, hood seams, and underbody in a controlled, high-volume spray. Inside, sensors and technician observers watch for any signs of water intrusion. Paper strips are laid in door sills and on floorboards to detect even the slightest moisture. If a leak is discovered, the vehicle is flagged and pulled off the line for immediate resealing and retesting. It cannot proceed until it passes the rain test with zero leakage. This step is especially crucial for a vehicle like the Land Cruiser, expected to withstand deep water crossings and monsoon conditions around the globe. Once water testing is complete, the vehicle is dried using high-volume air dryers and microfiber towels, then passed into the dynamic testing line. This portion of the plant is built like a miniature test track and includes a chassis dynamometer, suspension shakers, and NVH test chambers. The vehicle is driven onto rollers that simulate different road conditions: smooth asphalt, coarse gravel, cobblestones, and even railroad-like rumble strips. Sensors embedded in the seat rails, firewall, and steering column measure vibration amplitudes and frequencies. Technicians inside the cabin listen and feel for buzzes, squeaks, or rattles, often called BSR defects. These can originate from loose trim clips, misaligned panels, or improperly torqued fasteners. If a defect is detected, it is logged, and the vehicle is removed from the line for diagnostic teardown and correction. The expectation is not simply that the Land Cruiser should function, it must feel cohesive and solid, like a single carved block of steel, even when driving over rough terrain. Following dynamic tests, the vehicle undergoes wheel alignment and headlight aiming. On a laser-guided platform, cameras scan each wheel to measure camber, caster, and toe angles. Adjustments are made to the suspension arms or steering links via automated or technician-guided tools until alignment falls within specifications. Proper alignment is vital not only for tyre longevity and handling performance, but also for safety systems like lane keeping assist, which depend on accurate steering angle input. Headlights are tested and aimed in a separate chamber equipped with photometric sensors. The Land Cruiser's LED or projector headlights are precisely leveled and oriented to ensure they illuminate the road correctly without blinding oncoming drivers. Adaptive lighting functions are activated and checked for smooth operation, whether swiveling into corners or dimming individual LED segments during oncoming traffic. From here, the vehicle moves to the ADAS calibration zone, a critical step in preparing modern vehicles for road use. Advanced driver assistance systems, such as automatic emergency braking, lane departure warning, adaptive cruise control, and pedestrian detection, require that cameras and radar modules are perfectly aligned and calibrated. In this dedicated bay, high-resolution printed targets and reflective calibration boards are positioned at precise distances from the vehicle. The onboard systems scan these targets to calibrate the field of view, depth perception, and horizontal axis of the forward-facing camera and millimeter wave radar units. Any error in calibration can lead to inaccurate distance measurement or false triggering, so the process is repeated multiple times and verified using test data. The calibration results are uploaded to a central database that tracks the configuration history of every vehicle produced. This data can later be accessed by dealerships during servicing, ensuring traceability and long-term system accuracy. Now that every system is validated, the vehicle proceeds to the final software, flashing and configuration bay. This is where the Land Cruiser's onboard ECU cluster is updated with the most recent firmware, software maps, and region-specific settings. This may include engine management tuning for specific fuel grades, transmission behavior mapping, infotainment localizations, navigation system data, and wireless communication protocols such as Bluetooth, Wi-Fi, or connected services. At this stage, factory technicians also activate region-specific compliance features, such as emissions readiness flags, alarm system settings, and telematics modules, depending on the target market. Each configuration is verified with a scan tool and signed off electronically, with the software build number recorded in the vehicle's internal logs. Only now does the Land Cruiser approach what is known as the final release gate. This is the symbolic and operational point at which the vehicle is officially deemed complete. The engine is shut off, the ignition keys are programmed and paired to the immobilizer, and the factory build manifest is printed and affixed to the dashboard. Every vehicle is tagged with a VN, barcoded for traceability, and matched to its build sheet, which includes options, colors, production dates, and destination data. Before the vehicle exits the factory floor, it passes through a dedicated detailing and protection zone. Here, trained specialists give the vehicle a final clean, polish, and inspection under soft lighting. Protective plastic films are applied to vulnerable surfaces like door sills, bumpers, infotainment screens, and seat cushions to prevent damage during transit. The tires are overinflated slightly to accommodate potential temperature or pressure changes during storage or shipping. Depending on destination, vehicles are either driven under their own power to a nearby staging lot, loaded onto enclosed transport trucks, or, more commonly for international orders, driven onto open-sided auto carriers headed for port. Some models are even driven short distances onto roll-on roll-off cargo ships where they're carefully parked and secured by maritime handlers. Toyota's global logistics system then routes each vehicle to the appropriate country, dealership, or fleet customer, with continuous tracking from the moment it leaves the factory. With the Toyota Land Cruiser now fully assembled, inspected, and officially cleared through the final quality gates, its departure from the factory marks not an end, but the beginning of an extraordinarily managed logistical operation. Every vehicle that rolls off the production line is immediately tagged for traceability and assigned a specific post-factory journey depending on its model variant, trim level, destination market, and regional compliance standards. This downstream supply chain is as complex and meticulous as the assembly process itself, ensuring that every Land Cruiser reaches its customer without compromise. The first stop for many newly built Land Cruisers is the factory's outbound vehicle staging area, an expansive, organized expanse of tarmac where hundreds of vehicles are arranged in neat rows, each aligned with specific shipping designations. From here, Toyota's Vehicle Logistics Control Team coordinates batch deployments of finished units either to inland dealerships via transport trucks or to international ports by rail or by direct carrier convoys. In Japan, for instance, production centers like Tahara or Yoshiwara route large volumes of Land Cruisers to export terminals in Nagoya or Yokohama. These vehicles are often earmarked for overseas regions such as Australia, the Middle East, Africa, or North America, markets where rugged off-road capability is highly valued and thoroughly tested. But before these vehicles are loaded onto ships or trucks, they undergo port preparation processes that further ready them for transport and market compliance. Many Land Cruisers, especially those headed abroad, are sent to a vehicle logistics center adjacent to the port. At the VLC, they undergo a multi-step check involving additional accessory installation, protective film removal, and localization. In this phase, market-specific options that cannot be practically installed on the main assembly line are added. These might include tow hitches, roof racks, side steps, navigation system SD cards, language packages, or customer-requested extras like off-road kits, underbody protection plates, or integrated dash cameras. All installations are performed by certified technicians using torque-verified tools and original parts. Any deviation from standard configurations is meticulously documented to preserve the vehicle's warranty and certification status. Equally important is the post-assembly compliance verification. Each region around the world has unique emissions, safety, and equipment requirements, and Toyota manages this through VN-specific programming. For example, a Land Cruiser bound for the United States must meet Federal Motor Vehicle Safety Standards, California Air Resources Board regulations, and NHTSA labeling, while one going to the UAE must be equipped with Gulf-specific cooling systems. stronger alternators for heat tolerance, and Arabic language infotainment settings. Once localized and cleared, the vehicles are lined up for Ro-Ro shipping or loaded into multi-level vehicle transporters, depending on whether they're being exported overseas or moved overland. Ro-Ro ships, purpose-built for automotive logistics, feature vast internal decks that resemble floating parking garages. Each vehicle is driven onto the ship under its own power, guided up loading ramps and secured to the deck using industrial tie-downs. Toyota limits engine runtime during this stage to reduce emissions and fuel consumption, and each vehicle's onboard diagnostics are scanned one last time before the cargo bay is sealed. While en route to their destinations, Land Cruisers are tracked using global supply chain visibility platforms that integrate with GPS and customs data systems. Estimated time of arrival, environmental exposure logs, and any transit anomalies are recorded to maintain full accountability. In the case of sea freight, average journeys can last anywhere from 7 to 45 days, depending on distance and port congestion. Throughout that time, Toyota's regional distribution hubs prepare to receive, inspect, and redeploy the incoming vehicles. When a shipment of Land Cruisers reaches its destination country, it undergoes a pre-delivery inspection at a regional Toyota import processing center. Here, the vehicles are unloaded and immediately examined for any cosmetic or mechanical damage incurred during transit, such as scuffs, dings, or tie-down abrasion. Battery voltage levels are tested, tire pressures are corrected, and all protective films and covers are removed. A diagnostic scan confirms system integrity, firmware versions, and mileage. Even the odometer reading is logged to ensure compliance with regulations about mileage disclosure. At this stage, additional final touches are added. Owner's manuals, registration documents, floor mats, and dealer-branded accessories are placed inside the cabin. In some regions, local emission or safety stickers are applied, and temporary license plates are affixed for legal transport to dealerships. Once cleared, vehicles are grouped by dealer destination and loaded onto regional delivery trucks that will carry them directly to showrooms. Back at the dealership, the Land Cruiser receives one final inspection, this time by the sales and service staff, who perform a customer-facing version of the PDI. They check for cosmetic perfection, start and idle the vehicle, activate climate controls, sync the infotainment system with local maps and language settings, and validate that no error codes have appeared since transport. Only once this process is complete does the vehicle become available for customer viewing, test drives, or delivery. But even after the vehicle reaches its owner, the story of the Land Cruiser's production process continues. Part of what makes this model so revered is the rigorous pre-production durability testing and engineering validation that underpins its design, much of which occurs far from the public eye, long before mass production begins. Toyota's quality assurance team performs global field testing of pre-production Land Cruisers in some of the harshest environments on Earth. These are not just theoretical validations. They are full vehicle stress tests that replicate real-life torture scenarios. Endless hours of corrugated dirt roads, deep water fording, freezing temperatures, desert sand climbs, and sustained towing at maximum payloads. Test mules are equipped with telemetry and stress sensors embedded into suspension arms, chassis, weld points, engine mounts, and transmission casings. Engineers collect terabytes of data across thousands of miles of field testing, looking for signs of fatigue, thermal breakdown, or structural deformation. Some of these test vehicles are subjected to frame twist tests on purpose-built platforms that simulate extreme diagonal wheel articulation. Others are parked in cold chambers for overnight freezes, and then started without preheaters to evaluate cold start behavior and electronics resilience. Brake systems are stress tested down alpine gradients with full payload, while fuel systems are evaluated in high-altitude passes to ensure vapor lock prevention. Every component, from seat foam density to door hinge lubrication, is analyzed, tested, and reworked if it fails to meet Toyota's standards. Once the prototype phase ends and the production design is finalized, Toyota invests in a global supplier quality control network to ensure consistency across all materials entering the factory. Every bolt, sensor, harness, and panel delivered to the Land Cruiser production line must meet ISO TS 16949 and Toyota's own global supplier requirements. These parts are tagged with barcodes and batch numbers that trace their entire life cycle, from material sourcing to delivery. In the event of a future defect or recall, Toyota can pinpoint the exact day, shift, and supplier lot that produced the affected component, allowing for rapid response and recall management. Even paint batches, foam chemical blends, and adhesive curing cycles are tracked in real time. Many Land Cruiser parts are over-engineered compared to industry norms. For example, frame cross members are often hydroformed, resulting in stronger yet lighter weld-free shapes. Fasteners on critical joints are not only torqued, but angle checked with digital sensors to ensure the proper stretch and clamp force. This over-engineering is not excess, it's strategic durability. And in keeping with Toyota's core philosophy of Kaizen, or continuous improvement, feedback from real-world usage informs future iterations. Engineers regularly review warranty claims, service center data, and owner feedback. If patterns emerge, such as premature wear on a bushing or corrosion on a bracket, adjustments are made on the production line, sometimes within days. This responsiveness is one reason why even aging Land Cruisers remain reliable long after newer competitors have faded. As the modern factory evolves, so too does the way the Toyota Land Cruiser is built. While the foundational principles of reliability and mechanical toughness remain unchanged, the methods by which these values are achieved have transformed dramatically over the decades. In this next phase of the journey, we step deeper inside the plant, not just to observe physical assembly, but to understand how the Land Cruiser benefits from one of the most advanced manufacturing ecosystems in the automotive world. At the core of Toyota's approach is the Toyota Production System, a manufacturing philosophy built on lean principles, just-in-time delivery, jidoka, and continuous improvement, or Kaizen. The production of a Land Cruiser represents one of the most intricate expressions of TPS in action, balancing high-mix, low-volume builds with exacting consistency. Unlike high-volume sedans or economy cars, Land Cruisers are often built to order, customized by region, and produced in lower quantities, demanding exceptional flexibility from the factory floor. That flexibility is enabled by Industry 4.0 technologies, a suite of digital tools and automated systems that allow each vehicle to be uniquely tracked and built in sequence. As soon as a Land Cruiser order enters the system, a digital production order is generated and encoded into what Toyota calls the build manifest. This manifest travels with the vehicle in both physical and digital forms, informing every workstation along the line exactly what variant is approaching, the trim level, drivetrain layout, regional settings, colors, accessories, and emissions package. Throughout the factory, a network of programmable logic controllers and manufacturing execution systems orchestrate operations with incredible coordination. These systems communicate with RFID readers, barcode scanners, and vision recognition cameras that constantly monitor each vehicle's movement and configuration. Robotic arms that apply adhesive, install glass, or torque bolts adapt automatically depending on the model variant passing through. This seamless shift between configurations enables Toyota to build a diesel-powered Land Cruiser for the Australian Outback on the same line as a petrol V6 bound for a Middle Eastern fleet customer, without ever shutting down or retooling the line. In the welding shop, cobots, collaborative robots, work side by side with human technicians. While fully automated welding cells handle repetitive, high-speed tasks like frame seam welds or floor pan spot welding, more complex and nuanced joints are still guided by experienced hands. The cobots assist in holding parts, adjusting positioning, or applying filler materials, responding to slight shifts or tolerances that may not be visible to machine vision systems. These robotic helpers improve efficiency without replacing human intuition, an essential balance in Land Cruiser production. The paint shop is another showcase of cutting-edge automation. Here, electrostatic rotary bell atomizers precisely control paint flow and dispersion, resulting in incredibly fine droplets that adhere more evenly and waste less material than traditional spray systems. The robotic arms in this area are capable of mimicking human wrist and elbow movements, adjusting in real time based on vehicle height, curvature, and even ambient temperature or humidity. Every body is scanned before and after painting using laser profilometry, which maps the surface for thickness uniformity, gloss level, and micro defects invisible to the naked eye. But even with all this automation, Toyota continues to rely heavily on human craftsmanship, particularly in the trim and final assembly zone. Here, skilled workers, many of whom have decades of experience, perform tactile evaluations and intricate installations that machines still cannot replicate. These technicians are trained through Toyota's in-house Takumi development program, a mentorship model where junior assemblers learn directly from master-level craftspeople over years of apprenticeship. One example is seat upholstery. While much of the seat frame assembly is robotic, the final wrapping of leather or synthetic material is done by hand. Each seat is inspected for tension, uniformity, stitching consistency, and padding distribution. The goal isn't just functionality, it's comfort and luxury underpinned by durability. In markets like the Middle East, where sand, sweat, and heat stress interiors more aggressively, even the grain of the leather is tested for UV resilience and moisture rejection. Other critical human-controlled operations include dashboard alignment, door hinge installation, and seal compression fitment. These may sound minor, but in a vehicle expected to operate in extreme environments, the margin for error is virtually zero. An improperly seated door seal can lead to wind noise, water leaks, or dust ingress, issues that would tarnish the Land Cruiser's otherwise sterling reputation. Technicians use soft mallets, torque wrenches, and custom fit gauges to confirm that every joint, hinge, and gasket is within specification. In the realm of electronics and diagnostics, Toyota employs AI-assisted test benches to simulate hundreds of driving scenarios. As each Land Cruiser nears the end of the line, it is plugged into a comprehensive vehicle communication interface that links all onboard control modules to a centralized diagnostic system. Artificial intelligence algorithms analyze sensor outputs for anomalies, looking not just for outright failures, but for subtle trends that could indicate a future issue. For example, a window motor that draws slightly more current than average may still work perfectly, but the AI flags it as a possible early-stage failure, and the part is replaced before the vehicle ever leaves the factory. AI also plays a role in predictive maintenance of factory equipment itself. Every robotic joint, spray nozzle, and conveyor belt in the plant is outfitted with sensors that monitor usage cycles, vibration levels, temperature, and wear patterns. These data streams feed into a digital twin of the plant, a virtual model that mirrors the real-world state of every machine. When a critical component shows signs of fatigue or misalignment, the system alerts maintenance teams well before a breakdown occurs, minimizing downtime and preserving output quality. All these systems, robotic, digital, and human, work in concert within the framework of Toyota's Genchi Genbutsu philosophy, meaning go and see for yourself. Engineers, supervisors, and even executives are required to visit the factory floor regularly, interact with staff, and observe production firsthand. This cultural commitment ensures that management decisions remain grounded in reality and aligned with the conditions experienced by those who build the vehicles. The cumulative result is not just a product that's rugged or capable, it's a vehicle built with an awareness of its purpose, and a factory tuned to produce that outcome consistently. The Land Cruiser's legendary reliability is not an accident of design. It's the end product of thousands of discrete quality control decisions made at every junction in the factory's ecosystem. And Toyota's commitment doesn't end at the physical vehicle. Increasingly, post-sale digital infrastructure is integrated during production. Infotainment systems are loaded with over-the-air update capability, and telematics modules allow for remote diagnostics, GPS tracking, and performance monitoring. These systems are calibrated on the line and verified during end-of-line testing, setting the stage for ongoing connectivity and customer engagement long after delivery.